Welcome to this first afternoon webinar dedicated to the technical achievements of the Shift2Rail program. You are attending the session dedicated to the second innovation program of Shift2Rail, dedicated to traffic management and advanced train control. Before we are moving to the agenda and presenting the speakers for this afternoon, I wanted just to remind a few housekeeping rules for this afternoon. So you should be able to listen to me, hopefully, and you should be able to see what is on the screen. You cannot take the floor as attendees directly. But please use the raise hand function if you want to ask questions during the Q&A part at the end of each of the session. Alternatively, you can also put down your question in the chat, and I will be very happy to take these questions to our speakers and representatives this afternoon. We are on a tight schedule because we have lots of content to present to all of you this afternoon, and I want to make sure that everyone gets the chance to present properly and that all of you in the audience also get the chance to ask questions if you have any. So we are going to move very quickly to the first session. Just as an overview, we are going to have 8 specific presentations this afternoon that are representing 8 of the technology demonstrators of the second innovation program of Shift2Rail. And you are very lucky because we will be able to go through most of the achievements of Shift2Rail in this specific area this afternoon. And hopefully it will give you a good glance at where we stand right now after 4 or 5 years of research and innovation activities. So we're going to start with Adaptable communication system. This is the first technology demonstrator of Shift2Rail Innovation Program 2. It is dedicated to finding new and implementing new telecommunication for railways. The activities have started in 2016 and they are now reaching almost the end by standard of the program. And today I'm very happy that we have Ulrich Geier from Control and Marion Berbino from the University Gustave Eiffel, who will present where we stand in terms of achievements for this specific part of the work. So without further ado, I will give the control to Ulrich. Ulrich, you should be able to take the lead right now, and you have 20 minutes to lead us through the recent achievements.
Thank you very much, Leah. So
Ulrich, you are muted.
yeah. Can you hear me now?
Yes.
Okay, second try. So as Leah mentioned, I will speak about the first technical demonstrator 2.1, the adaptable communication system. And just after, Marion will follow about the project MO radio for rail. So let me give you first kind of content, what I would like to speak about. First of all, I will focus on the project status and achievements of the adaptable communication system. Then I will speak about the demonstrator lab test setup. You can imagine in those critical situations we are all in, how it was. It was a real challenge to make the lab tests. I will speak about the list of new innovations, and finally the collaboration with the UIC project FRMCS, Future Railway Mobile Communication System, towards the CCS TSI 2022. After that, Marion will speak about MO Radio for Rail, the project objectives and the results. A common outlook will be given just after, and then, if everything works fine, which I hope, you will see a small film from Marion about Emo Radio for Rail. So let me focus on the project status and achievements. Some of you have maybe joined already in the morning the session from these info days, and in the coffee break, if you have not taken a coffee, you would have seen some films, and one of the film was for IP2. It was animation film of the adaptable communication system, where we at the end have shown the achievements, which was the user system requirement specification and as well the system specification. Within Shift2Rail 3, we have updated both to stay in sync with the requirements coming from the different work packages and projects, especially also to stay in sync with the external UIC project FRMCS. One of the main activities in Shift2Rail 3 about this technical demonstrator were the lab tests. So we have here 3 technical demonstrators to be tested in a lab. One for high-speed mainline, led by Thales, one for regional freight, led by Hitachi, and one for urban suburban, led by Siemens. We had 2 deliverables in this phase. The first one is update of the prototype development report, showing which kind of development was done for the prototypes, which are part of the demonstrators. This is already available, but confidential. Second one is also confidential and nearly available. So we are here in the last review cycle, and it will be available according to the plan in November this year. The next point is the field test strategy, because lab test is one thing, but we want to go out and test the adaptable communication system concepts in the field. Therefore, the focus will be on the field tests in Shift2Rail 5. We have agreed on the field test strategy. This document is already available, and it will be for sure soon uploaded also to the Shift2Rail webpage, because it's a public deliverable. Furthermore, due to the complex system with a lot of functions and features, we have to look on innovative antenna system, which we did. We have made a report out of that, which is also at the last review stage and will be available according to the plan latest next month. At the bottom, you can see all the partners which are in this work package 3. And I'm really happy and proud to have all these partners in, to be honest, because there were a lot of fruitful, creative discussions which led to a long list of innovations, which I will show in some of the next slides. Demonstrator lab tested up. As I said, in this very difficult situation, we wanted, the original goal was to be all in one lab, at least from demonstrator point of view, from technical demonstrator point of view, but that was not feasible. So first approach was to interconnect all the labs and leave the prototypes where they are. But then the next step happened that even the company people couldn't go to their own labs. So we have to implement remote testing towards to the labs. And this was fortunately possible, so that at the end we have achieved the common objective. You can see on the right-hand side the structure, the architecture of the lab test setup. On the top, you can see the real applications, the application emulations, and the data at the track side connected through the central network to the adaptable communication system units. So the brown boxes are the ones under test. In the bottom, you can see more or less a mirrored architecture as well, with the real applications now on the train, on board. Also emulations and the data related to that connected via the train network to the onboard adaptable communication system. We had a lot of radio access technologies. We had the SATCOM, we had Wi-Fi, we had public LTE, we had dedicated LTE. But on top of that, we had network emulators to also test some disturbances. We had RF emulations, and I think this specific 2 parts will be shown just after by Marion about Emo Radio for Rail. So with the help of the remote connections of the different labs, the usage of the simulators and emulators and restructuring of the test cases, we have fortunately achieved the objective. I would like to speak about now the innovations we have been developed during the project time. So the adaptable communication system in the middle, we are now able to support multiple applications in parallel. So voice and data in parallel, which was not possible in the past. With the new system, we are transparent from application point of view. So the applications is asking for data throughput, asking for latency, quality of service, and then they do not have to deal how the data is going from the train to the track. Everything about that will be done by the adaptable communication system. We will have a higher data throughput and simultaneous connections because we are using a couple of bearers in parallel, which leads to the fact that we are more reliable through this higher redundancy, and the connection is improved. The whole system is dynamically selectable, which means the applications can also change their quality of service requirements. We are radio access technology agnostic, so we are also leave the door open for upcoming new radio access technologies to be able to integrate it into our system. We have looked at a range of business models. For example, when we think about communications, non-critical communications, passenger informations, we want to be able to support them as well. So we have looked at business models with public MNOs. We have looked at new antenna systems, and finally, we have facilitate the migration. So that are the innovations so far, and I'm looking forward to add additional ones in the next project. Collaboration with the UIC project FRMCS is very important for us. Why? Because the project FRMCS, Future Railway Mobile Communication System, is the one which defines the new communication system, which will write the documents which will be referenced in the CCS TSI 2022. On the right-hand side, you can see the way we collaborate. We have already aligned the user requirements spec. On the left-hand side, you see the UIC documents, the functional requirements spec, the system requirements spec, and on the right-hand side, the different activities we are doing in Shift2Rail with the lab tests, with the field tests. You can see a lot of errors in between, which shows that we interwork and review each other. At the end, we will have the FRMCS system specification available, which then will be referenced in the CCS TSI. That's all I wanted to talk about, and I want to give now the voice to Marion for the second part.
Okay, so I will go quickly on the slide of the Emul Radio for Rail project, which is a project related to ACS communication with an open call. The project objective was to develop an hardware and software emulation platform representative of railway environment to evaluate the performance of the different prototype Uli told about. So the partner was University of Lille, Radio Labs, Metro Madrid, Ikerlan, Technical University of Denmark, Ernex, and Université Gustave Eiffel was leading the project. With discussion with colleague, Uli, next. Okay. So with the discussion with a colleague from WP3, we focus on different radio access technologies, two LTE, one private, one public, satellite, and Wi-Fi. So as you can see, we have several possibilities, emulation at radio level environment, so at radio connection, and emulation at IP level. Next.
You actually have the control, Marion.
Ah, okay. So I control with my, okay. So we have selected a lot of railway channel environment. You know that railway channel environment are very different. So we did a huge literature survey to have radio channel to be able to be emulated with different speed and different Doppler. And we have also developed, thanks to research collaboration, a specific model for tunnel, because you have quite no model in the literature. So you have here the different bricks that we have integrated then. So we have one brick based on open air interface platform, to emulate LTE system. It could be FDD or TDD. We have also the possibility to emulate thanks to Rode short equipment. Then we have a very simple system with Wi-Fi access point, and then the complete satellite network emulator developed by Radiolabs. Here you can here you can see the different platforms, so you will see better in the film. Here you have the integration at Ikerlan Lab with the channel emulator and one LTE platform. Here we have the second one, and here's the Wi-Fi platform with injection of different type of interference. Here on the table you can see the two LTE platforms. And on this part, you can see the box, which is the satellite channel emulator from Radiolabs. So the principle is that we did a lot of lab tests to have finally model. So we can have the experimental assessment of the different bearers. And then we have also the variation or the statistical variation of the different IP parameters, such as bit error rate, jitters, bandwidth, regarding the different radio channel environments. So here you have the complete integration of the system, which was done at IRSICA in Lille before going to Siemens lab. And thanks to a nice cooperation of Keysight, which allow us to have the sufficient number of channels, because at the beginning of the project, it was planned only one LTE. So if we want to emulate at the same time two LTE, one Wi-Fi, and the satellites, we need a bigger equipment than the one of the colleague from Ikerlan. Okay, so Uli, you can have the conclusion, and then you will see the small film after.
Okay, let me start with my conclusion. So we are really well on track, looking forward to the next step, to Shift2Rail 5. We have created a couple of innovations which I've shown. We have a really good cooperation with the UIC project FRMCS. We're sitting in the same boat, going in the same direction, which is, I think, fruitful for both of us. We have validated the technical demonstrators and prototypes, and are really looking forward to focus now to the field tests of the demonstrator on Shift2Rail 5.
And then for Emul Radio for Rail, we have developed all the bricks plan in the project. So we have a nice proof of concept. Everything is working. We experienced some difficulties because open air interface is not planned at the beginning for very long test, and then we are ready to integrate with different industries. So a first integration has been done remotely with Hitachi, and we plan a real integration in Germany with Siemens. And we are also working for a remote, possible remote integration, but we are afraid of the delay injected by the by internet. So next, Uli or myself. So I am pleased to show you a small film. I hope it will work.
I hope so too.
The Emul Radio for Rail project is a European collaborative project financed in the framework of the Shift2Rail program. The partners of the project are Université Gustave Eiffel, Université de Lille, Denmark Technical University, Radiolabs, Metro de Madrid, Ikerlan, and Ernex. Université Gustave Eiffel is leading the project. Today, a new wireless communication system for control and command of trains based on radio communication is under development at European level. This new system will concern every kind of train, high-speed train, intercity, freight, regional, and metros. This system, called Adaptable Communication System for all railways, will operate in parallel several radio access technologies. The test of a new wireless communication system in real condition on the track is very expensive and very long. New systems should be validated without expensive trials. To do so, this approach is called zero on-site testing. The EMU Radio for Rail objective is to answer the challenge of zero on-site testing. To do so, we have developed a hardware and software platform for the test of new communication system prototypes. The aim of the EMU Radio for Rail project is to emulate the complete link from the equipment on the train to the network on the ground, which corresponds to the uplink, and vice versa, that corresponds to the downlink, and then to mimic the real radio environment with a channel emulator. The radio railway environments are very different, and the waves behave differently. This behavior should be taken into account for the system development. Mathematical channel models are obtained thanks to measurements along the track and are able to reproduce the statistical behavior of the channel. They are then implemented in specific device called channel emulator. The platform includes one satellite system emulated at IP level developed by Radiolabs in Italy, two full LTE systems developed with open air interface software, respectively by DTU in Denmark and Université Gustave Eiffel in France. The two LTE systems are frequency division duplexing. They operate in the same band. Then we have one Wi-Fi system with two independent modems, one on the ground, one on the train, operating in time division duplex, developed by Université of Lille and Ikerlan in Spain. And then perturbation can be injected with external jammers or signal generator, or directly in the channel emulator. Now, we will detail one open-air interface platform. Here is the dongle that mimics the user equipment in the train. The dongle is connected to the eNode B via the channel emulator. The eNode B mimics the USRP board connected to a computer and to the Evolve packet core emulated by another computer. Here we can see the IP transmission between the eNode B and the user equipment in the train through the channel emulator with a specific Illy-Terrain channel model. The project has selected a set of 5 specific channel models for railway environment, including tunnels. We have verified that each platform works correctly individually in each partner lab. A big challenge was to integrate all the bricks of the platform together in a unique location at Irsika and to connect all of them to the Keysight channel emulator with the right setup. The next big challenge is the integration with industrial communication system prototype from Shift2Rail 3 WP3 project. Then the platform will be available for testing. The platform will be then upgraded to take into account 5G deployment. It could be easily transported to automotive domain with the right channel models. I would like to thank all the partners of the project for the fruitful collaboration and the fruitful discussion. I would like to thank the Shift2Rail 3 WP3 partners for the discussion, and obviously I would like to thank the European Commission for the financial support.
Thank you very much to both Ulrich and Marion. I forgot to mention that Ulrich is from Kontron and he's the leader of the adaptable communication activities inside Shift2Rail, and Marion is the coordinator of EMU Radio for Rail. And if you are a bit expert in this domain, you know that they are both very well known and renowned. You both finished right on time. Thank you for this. I'm trying to see with my colleague apparently we do not have yet questions in the Q&A, but I'm looking into the participant in the audience. Again, I remind you, if you want to ask a question, you can just raise your hand and I will open the mics for you to ask a question. Don't be shy. I know this is the first session, but if you want to ask a question, you can do it now. This is the best occasion. We have both experts online with us. No question at all. Okay. I see one hand was raised. And this hand is not raised anymore. Okay.
I see one question.
In the chat, Leah.
There's one chat.
Yeah, it's Michael Meyer Zuhöster.
Maybe we can do what will be the next steps in communication for Adaptable Comms in X2Rail 5. So the next steps will really to go into the field. So all three technical demonstrators, which I've mentioned before, for high-speed mainline, for regional freight, and also for urban suburban, have planned to go into the field with the help of infrastructure managers to really test the systems in the field and to see if the concepts are really working. That's the main focus for X2Rail 5. And
this is indeed, like I was saying at the very beginning, we are moving towards the last part of the program, and indeed the next two years, and we will see it also for the next presentation this afternoon, really focusing into higher TRL activities and prototype testing and pilot lines. Definitely an important part of the program. Okay, so if there is no question, it's the last call. Then I suggest that we move to the next presentation. I thank you very much, Ulrich and Marion. Thank you for this, and thank you also for obviously the team of experts behind you, who is also working very hard on this topic. Next, we are moving to the second session, which is dedicated to moving block and to see where we stand in those developments. Key question around moving block is how do we increase capacity on the railway lines, especially in Europe? And this is a key concern for the railways and for the infrastructure manager in particular. This is a well-known problem, and capacity is one of the key challenges and the key objectives that we set ourselves at the beginning of the program Shift2Rail. Moving block is expected to be one of the key contributors to increasing the capacity onto the railway line. And I'm very happy that Simon Chadwick from Siemens, who is the TD leader for moving block inside Shift2Rail, that Simon is here connected with us today, and to lead us to presenting the latest achievements and presenting the next steps in this field. Simon, I give you the control, and the floor is yours for the next 20 minutes.
Okay, thank you, Leah. Yep, I think I can control now. Yes, okay. So I'm Simon Chadwick, as Leah's just introduced. So I'm going to talk about our TD 2.3 moving block in the context of Shift2Rail IP2. So just a little introduction to what I'm going to talk about. I'm going to give a moment take a moment to look at what we think the future railway might be like. Then I'm going to look at how moving block and how it fits into the ETCS world. We're going to look at what we've actually done within our TD 2.3 moving block, and a little bit how that links to the TSI 2022. And we will have a what next moment and a final conclusion. Okay. So to illustrate just to give an idea of that future railway, of course, there's many people who have been thinking about what the future railway would look like, but here is just one take on this. I've got a series of 3 slides. So this is a traditional signaling railway with fixed blocks, with color light signals, with trackside train detection, which can be axle counters, track circuits. Very likely there's some national train protection system shown here. And one of the key attributes of this is that the signaling is hard coded into the railway infrastructure in some way, either by positioning axle counter heads or by block joints for track circuits or similar. So then we might step onwards so that we end up with a level 2 system. This is already present in the standards today in the TSIs. So we might have, might be able to take away all the signals, have block markers instead, marker boards. We have, we can then have a standardized, if you like, ATP system. We don't need the national train protection system anymore. But I do need to add some things. I have to equip my trains with ETCS on board. I have to add some balises to the trackside, ID in a communication system, and I have to extend my trackside signaling system to include the radio block center. So far it's possible today. What we're looking at for moving block is the next step, which is that we take away some more things. We take away the dependence on trackside train detection, which actually removes the hard coding of the signaling into the railway infrastructure. It's a much, if you like, softer approach in terms of the fitting to the infrastructure. However, I have needed to add some more things. I've had to add the train integrity monitoring system, shown as TIMS, to the trains, and I've had to upgrade my interlocking and RBC type system. Now, if you take this, this is going to now make maximum use of the infrastructure for trains with minimum infrastructure in terms of signaling fitted to the railway. And if you take all this together with the other topics like using ATO, like a much smarter traffic management system, I then begin to think about what the future railway may look like. And then this is ultimately, if you take all these, you reach the Shift2Rail KPIs of increased capacity and increased reliability and reduced cost. Okay. So that was a future staring moment, just to try and give some idea. How does this fit into ETCS? There's quite a quick answer to that. Moving block in ETCS is ETCS level 3. Some parts of this are already defined, but not all. And that's the key to our work, the work we've been doing. I've highlighted here some of the biggest issues. So the biggest issues about the reporting of train integrity and how it's processed, how to react when train integrity fails. Another big issue is the removal of the trackside train detection, or at least some of it or all of it. And the other thing that then becomes true is I'm now dependent on algorithms in the ETCS trackside to maintain that awareness of the track state, including under failure conditions. So if a train stops talking to me, I must remember that it's there, and so on. One of the issues was part of our work we've come across here is that we are now specifying the behavior of some of the aspects of the level of the trackside signaling system, but actually in ETCS level 2, that isn't really specified. The interfaces are very well specified, but not the actual behavior. Well, that's a sort of issue, if you like. So I'm now going to give you a summary of what we've been doing within TD 2.3. We've been present in X2Rail 1. We're working today in X2Rail 3. And I will in a moment also talk about what's the next steps in X2Rail 5. So in X2Rail 1, this is now finished. We took the ETCS baseline 3, release 2. We took this change request 940, which is about the processing of train integrity data. And we came up with some specifications and operational engineering rules, a preliminary safety analysis identifying some hazards. I put down the right-hand side some headlines from this work. One was the decision very early in the process to include systems with at least some trackside train detection, as well as systems with zero trackside train detection. A result of that, we ended up with these 4 different system types. So they're shown in the little diagram to the bottom right. So the full moving block with no train detection, the full moving block with some trackside train detection, And then the alternative arrangement for the moving block is to have these fixed virtual blocks. And the subtlety is that the movement authority is now to the rear of the occupied virtual block. And this again can be with the trackside train detection. All the deliverables from XtraRail1 are published on the XtraRail website, and they're all publicly available, the ones shown on the screen now. So next, we're now working in XtraRail 3, and we have 4 deliverables to create. The first one about testing of moving block systems is already done. It's not yet public, but it's delivered from the work package. The big deliverable here is actually our enhanced system specification. And so there's quite a lot of work still going on now to increase to improve the system specification. I'm just going to explain a little bit how we're doing. The target for this is in November. So that's a little challenging target, and it's taking a lot of the time and effort for the people involved in our work package. So this is a summary of the work we've been doing within our XtraRail 3 work to get to that deliverable. We have taken the results from XtraRail 1. We have looked at, I think it's 14 different use cases, which are listed down the left-hand side, to try to, if you like, verify or validate the requirements that were written in XtraRail 1 documents. We've also picked up a number of topics where we've spent some more time and effort looking at them specifically. So how do margins work, how the track state system works, what data must be stored, and propagation. And as a result of that, we're refining the results from XtraRail 1 to make our deliverable from XtraRail 2. And so there's quite a few workshops and things have been involved through this process. And we're in the last steps of this. We're actually updating the document ready for release, we hope soon. We have had some discussions with other TDs within the Shift2Rail, but actually the key contact has been with TD 2.5, the train integrity. Here we've had joint meetings. We've discussed how the requirements for train integrity input to the signaling system will work. We've discussed also the requirement for measuring of train length. And we prepared a joint response to a very old change request about train integrity. Let's see, the change request 149, where we looked at 2 different options to answer that. Okay. Nope. Yes. Okay. I'm going to talk a little bit about track state because that's actually exercised a lot of our time and effort. I'm going to show some examples. I just need to move this toolbox over there. All right. I'm going to show some examples. They're all going to use this type of diagram. They're going to use black as the railway line. They're going to use green for an area of track that was reserved for a train. They're going to use red for an area of track that's occupied by a train, and blue for an area where the trackside doesn't know whether there's a train present or not. So by inference, the ones that have no color on the here are clear. The trackside knows there is no train. And all these examples are going to be the full moving block type of examples. There's a long list of examples down the right-hand side. We don't have time for all of them today, so I'm just going to choose some. So here we have. So we start with one train. It is showing where the track is occupied in the trackside view of the world. And in the trackside view of the world, the amount of track that's occupied is longer than the train because of the uncertainty in the odometry. We also have the green part that's reserved for the train to move, and then the train can move. And if it's moved, it will send a train position report. It will then, the trackside will update its view of the railway and move its view of the train. And this process can repeat. And similar, the train sorts its position, the trackside updates its thought. Now, the next thing might be that the trackside will extend the movement authority. For another route maybe, and the process continues. Okay, so we get then the train position report and the trackside updates. Okay, so that's one train on its own. That's probably, as an introduction, it's a good start, but we're going to do some different ones as well. we're going to look at happens when I have two trains diverging from each other. So here's my two trains. They've both got their trackside knows where they are. They've both got reserved areas where the trains are allowed to move to. And I'm going to combine some of these steps now. The other thing that's important here in the full moving block world, we had to engineer some places where I will release the infrastructure behind the train. You will see if the trains now move, then they send position reports, and then the trackside will update. Yep, the trackside will update. You will notice that the authorization for train 2 has not gone past this marker board because it's going to go a different path. And then the trains can move some more. They will report their positions and the trackside will update. And now something interesting has happened because train 1 has passed this engineered release point. And so that means that I can actually set the alternative route for train 2. And yes, the representation of the reserve for train 2 is now, and that will be transmitted to the train, and the trains can continue on their way, much as with one train, but there's just two at once, and they're not interfering with each other anymore. Okay. One more click there. All right. So that was to illustrate two trains diverging, but I skipped now to some of the error conditions. We're going to look at loss of train integrity. So here's one train. It's moving. It's going to send a position report. And when it does so, it says, I've lost my train integrity. What will the trackside reaction be? It will now actually say that the track state is unknown, all the way from where the rear of the train was last reported up until the current front of the train. This whole area is now treated as unknown. The train might still be moving, depends on the reaction on board. If it does so and sends another position report, I still not moved the rear of the train. Whoops, sorry. One more click. Yeah, okay. I've still not moved the rear of the train, of the place that's unknown in the trackside view of the railway. We can play the same sort of thing with the loss of communications. So here's a train. It's moving. It's not going to send me a position report. It's moving. It's still not sent me a position report. And then after some time is involved, which are part of the work we've been doing to look at how this works. The trackside decides, I don't know about this train anymore. It must be somewhere between where it last sent me a position report and the end of the authority where it was previously allowed to move. So the track state becomes unknown up until the end of the authority, and the rear of this unknown part remains where it was last confirmed. Just, yeah, the reserved area, the other part of this is that the reserved area is no longer reserved for the train. It's just somewhere in this part of the railway. Okay. What we just described is the reaction of the trackside to the loss of communications. There's another whole story which is already present in this baselines that are already published about the reaction to of the train to loss of communications. This part we've been examining is what is happening within the trackside view of the world and its track state. Okay. So that's the example I was going to look at. We'll keep the others. Let's just change our topic just a little bit to how this fits with the TSI 2022. So we've done a little bit of work with our XRail 3 on the change requests I mentioned earlier, together
5
with
minutes.
yeah, okay. Yeah, a little bit of work on our the change request I mentioned earlier. We've been liaising with different bodies within our world we live in. So with UNISIG regarding the safety change request, and with the RTMS user group regarding some new change requests. We actually have made some provision in our work for XRail 5, I'll talk about in a moment, for working on materials of TSI. So this is X2Rail 5. What we'll propose should start in December, all being well. And then we will take our results from X2Rail 3. We'll make some more results, updates, possibly for these newer change requests, which are enhancing our moving block world, and also do some more work on the TSI material. Okay. Also in X2Rail 5, we're planning to include this integrated technical demonstrator. It's only partly to do with the moving block parts. So we took 3 different TDs here, the TD 2.1 communications we just heard from Uli. We've got the moving block part and the train integrity part, and they're each got their own separate demonstrators. But later in X2Rail 5, towards the end, we expect to bring these all together in a demonstrator. And here's a picture of what we're planning to do. We're planning to have 2 trains. This is on the infrastructure owned by Network Rail in the test track. Planning to have 2 trains. We're planning to have the adaptable communication system Uli was telling us about. We're planning to fit with the train integrity system at least one of the trains from the TIMS TD. And we were then plan to have some tests like the happy day, one train following another, illustrating the moving block, the change of bearer for the communication systems, the loss of communications or loss of train integrity, the 2 so high level degraded cases from moving block point of view. Okay. So here's the conclusion. Here's that future railway vision. If we combine the moving block with the ATO, the traffic management, we have this future railway that's not hard coded into the railway infrastructure, where we can make maximum use of the infrastructure with minimum equipment. And we can combine this, as I said, with ATO, with traffic management, and have our future railway and head towards more harmonized operational rules by having a simpler system. I think that's the last slide. Yes, thank you. So how does that fit with the timing, Leah? Have I done?
This is perfect. Thank you very much. Perfect.
It's quite quick. So anyway, here we are.
This is good. Thank you very much, Simon, for this presentation. I'm looking into the chat. I'm looking into the attendees and see whether we have some questions. I see that there is
I see a question.
One question indeed. Is there a difference in behavior between unknown situation and occupied?
Yeah, so it's essentially the occupied, the trackside system knows there is a train and knows about the trains there. The unknown, there could be a train or maybe there isn't a train, or if there is a larger area, it's there somewhere. And this how it's handled is differently. I cannot have a full supervision, so full speed movement authority in an unknown area because I might collide. So if the system would provide you with an on-site movement authority, if you have to enter an unknown area, that was a sweeping, it might be the other word that's used there. I didn't do that example, but that's how it would work. There may be other ways to remove the unknown. For example, if you have some TTD, trackside train detection.
Yeah. Clear. I hope it answers the question from our attendee. If not, don't hesitate to follow up on that. Do we have any other questions? Someone wants to speak, maybe? Would they are speaking in front of everyone? No, I guess everyone is still a bit shy. I have a question for you, Simon, while we wait.
Oh, okay.
Maybe just to launch the debate. I think it's well known in the community that there was a few years ago specifications developed by the infrastructure manager for a transition, let's say, state called hybrid level 3.
Yep.
Can you maybe tell us whether it's been considered by Shift2Rail, discussed, and how all of this actually fits together?
It's been considered some. There is ongoing discussion. It is actually fits with one of the system types we had mentioned right near the beginning. So the system type that has fixed virtual blocks, that has trackside train detection 100%. So I can see, we see this as a step, as one implementation, and there's some current work, which we'll do next, to look at how we, the relationship between these two. Yeah. So yeah, some interaction, more to do.
Yeah.
But it's how you would migrate from this hybrid level 3 system to a system without 100% or train detection is one of the topics for discussion.
Yeah.
Which is where people want to reach.
Yeah, absolutely clear. There is a question in the Q&A. It was asked 1 minute ago. It is from Amazon and says, with what frequency is the status updated?
Okay, so this depends how often the trains are telling you their status. So essentially the behavior of the trackside will be to update when it's told by the trains, when they send train position reports, and the frequency this will. Today, it can be quite slow, can be 5 seconds maybe. If we have all the results from the Adaptable comms TD, maybe this can be faster with the replacement communication system. And then, of course, it would be more precise. I don't know whether that answers the question, but.
I hope so. Otherwise,
yep.
I guess someone can react.
Yep.
We have another one coming in. I think we still have time for a couple, and then we'll have to go to the next presentation. It's a question from Alberto Manler asking, when do you think moving block will be mature enough for deployment? That's an excellent question, indeed.
Excellent question. Easy question, hard answer, I think. Well, that's what we all want to do. But I don't really know the answer immediately from my head as to when it will be mature enough. I suspect it will be in stages. I don't see a railway suddenly removing all its trackside train detection, for example, but maybe possibly via the hybrid level 3 that Leah has mentioned, systems where they have reduced train detection, or maybe areas where the plain track is without train detection. And I can see this taking some years, if I'm honest, to reach this point.
Yeah, there is always the question of, I think it's two different questions. There is the question of the maturity of the technology itself. I think considering that, and as Simon has mentioned, that we are planning to enhance the specification for ETCS level 3 in the TSI, we will do that, and with the absolute hope and assurance that the system and the specifications are mature enough for sure. Then in terms of the actual migration, this is indeed completely different and really depends on the actual needs on the tracks and the coordination with the railway undertakings as well.
Mm-hmm.
So I think we are we are just at the end of this session. Thanks a lot, Simon, for your presentation, and again, okay, also thanks to the team behind you who is active almost every day on this topic. We are going to move to the third presentation for this morning. We know, for this afternoon, sorry, we know that rail is a system of systems. We know that there are quite a lot of interactions between the different subsystems. Simon Chadwick has mentioned it in his presentation. For moving block to be fully enabled, we also need robust train integrity monitoring systems, and I'm very proud and happy to have Danilo Iovino with us from Hitachi STS, who is the TD leader on Teams, on train integrity monitoring system, and who will lead us through the specific achievements of this activity inside Shift2Rail. Danilo, you should have the control now. You can go ahead. The floor is yours.
Okay, good afternoon. Danilo from Hitachi, and we shall have a look to the onboard train integrity, TD. I'm trying to go in the, okay, next slide, okay. Onboard train integrity. We shall have a look to the scope of the work to the important specification activities and validation that we had. Also, we'll talk about demonstrators and simulators, cost-benefit analysis, and some quick anticipation about the chain length determination topic. Okay, scope of work in a glance. Just a few keywords. On board is the most important, which means implementing chain integrity without any interaction with the track circuit or Excel counters. Safe detection, but even false alarms filtering. We will see how this specific word has been reflected within the finite state machine. Also, addressing the existing freight wagons is part of the project, which means exploring wireless communication and energy harvesting. 3 years of work until now in Shift2Rail 2, still a couple of years in front of us in Shift2Rail 4. Up to now, 7 deliverables has been issued as planned. 3 of them are about specifications and are available in the project website as a public documentation, public deliverables. Important in this work was the collaboration with the moving blocks, as Simon said earlier. At the product level, interesting, fruitful analysis has been done with the adaptable communication to evaluate the use of the ACS gateway within the OTI context. Okay, the concept addressed, first of all, the definition of classes, product classes, based on some key features of the chain configuration relevant for the OTI system itself: communication, wired or wireless, power supply, or energy harvesting, ETCS present also at chain tail, and availability of data, kinematic data from the chain tail. Class 1 is focused on wired communication. Here we have an example, OTI device composed of one master in the cabin, the main cabin, front cabin, and one slave in the rear cabin. In this example, like in high-speed trains, for instance. In this case, the integrity criteria is based on just liveliness of the communication between master and slave over a wired network, like, again, examples Ethernet could be. Class 2, increasing complexity, which means addressing also the wireless communication. In the example of the freight trains, again, we have master device in the front cabin and a slave in the tail. Different integrity criteria, not just the liveliness of the communication, but also comparing kinematic data coming from the chain tail. The class 3 is about an increased complexity for additional functionalities, like, for instance, determining chain composition, also even chain length, which implies equipping all wagons. In this case, the integrity criteria becomes more about detecting separation between adjacent wagons. Okay, after this work of defining general features of the product of the OTI systems, the work focused on the specification, functional, first of all. The first aspect was to identify use cases, which is important to identify the high-level functionality. For instance, a couple of simple examples. The role of the OTI device depends on the active cabin and changes depending on the direction, and even also, for instance, depending on the presence of non-leading locomotive that can't be, although active, can't be slave. So it means having a mastership management. When on the right, when changing the chain composition, like in a joining situation, the OTI system needs to be reconfigured. We need always to have OTI master paired with the slave at chain tail. So the new tail after the joint operation need to be paired. This is in general the need of having an inauguration process. In the next slide, okay, now we can see how the finite state machine has been shaped, at least at high level. We've talked about mastership for the role assignment. You can see this high level picture. We have talked about inauguration phase to manage the changes in the chain composition. And then monitoring can start. The monitoring state has been designed in line with the change request 9040. In general, after an initialization step, we have regular, non-regular, and loss. Non-regular has been introduced for the false alarm filtering, the keyword we have seen earlier. Free values for the integrity, as specified in change request, confirmed the known and confirmed the lost and unknown, here used for the false alarm filtering. The change request 9040 implies for the TCS calculating the safe chain length, which is in the end the virtual occupation, based on last received confirmation. This was important, for instance, to evaluate which period to use for the reporting of this external device to the ETCS. For instance, it can be in the analysis done together with moving blocks, for instance, it can be between 5 seconds if we are in a low density situation, not more, not less than one, let me say 1 second in the higher capacity situations. Important is also the duration of the non-regular state, the filtering state. In this case, while in this state, the virtual length of the chain becomes longer. Important is a work still in progress in Shift2Rail 4 based on technologies and product classes to identify a good trade-off for a good rejection of the false alarms and anyway avoiding impact in the capacity for a too long virtual occupation. We shall have a look to this in the next slides. Interface. As also anticipated by Simon, a couple of options has been proposed. The base option ensures the compatibility, the full compliance with the existing specifications, which means just having confirmed the lost unknown, which means most important message is that we need, in case can be useful, an external dashboard to manage other information, like for instance, status of the device itself, or even the commands we have seen earlier to reconfigure the OTI system. We shall have a look to this dashboard in the demonstrators anyway. This is the reason why essentially the enhanced option has been also proposed to embed any information in a richer interface with the TCS and avoiding any additional dashboard, any separate dashboard for the OTI. This is in a few words the reason for proposing a couple of options. Next, okay. Formal validation was an important big work provided by Relenium that modeled the complete finite state machine for nodes in the most complex situation, like for instance in the intentional splitting. This work was very important to identify inconsistencies, deadlocks, gaps in the specification. The results has been embedded, integrated in the specification 4.1 and 4.2 that are available in the web, as I said earlier, and also to identify also hazardous scenarios and situations. This same environment in Shift2Rail 4 is being used now for the performance analysis to evaluate the duration of the non-regular state in different integrity criteria and different product classes. Okay, proof of concept, demonstrators and general simulation activities in the lab. 4 demonstrators. ASD since the beginning expressed an interest for the wireless communication, a direct link between tail and front cabin, exploring the feasibility in 3 different situations, 3 different positions for an antenna, on the basis of an installation analysis done in the beginning. In all the cases, these simulations showed that it was not appropriate, it was not good enough for the purposes. This is why this option was not explored later on, was discharged. And as there is now concentrated, even in Shift2Rail 4, on class 1B, wired communication, power supply available, master device in the locomotive, and slaves. Development is now in host environment and shall include also the possibility to simulate, to test in the lab, joining and splitting procedures with 2 trains. Let's go on. This demonstrator shall continue its work also on site testing. Next one. Also, Mermek in the beginning was interested to the wireless communication direct between tail and front cabin by using ultra-wideband, for instance. In this case, measurement activities has been carried out, and also in this case, with a different approach, the result was the same. No more interest in the end. In a first step, the interest was towards the GSMR, and later on, in a more general approach about the ACS approach, multi-bear radio that Uli has described earlier. Now Mermek is developing in host environment. The configuration is a chain with a TCS on both chain ends, classes 1 and 2. The panel, the simulation panel, shows how the OTI system can be configured to be master or slave, to be restarted. It is possible also to have a fault injection to observe the system behavior. And even next step this year includes the wireless scenario, which means class 2 criteria still in the lab in this phase. We are in the TRL 4 this year still. Hitachi demonstrator started with the class 1 ETCS on both chain ends. Here we can see an example of OTI dashboard, external dashboard, because this is a solution that is compliant with the base option. So this is a situation where additional information means not only the status, but even the integrity status, but the status of the device, if it is working or not, a couple of buttons to reconfigure the OTI system after changing the chain composition, joining and splitting procedures, for instance. Development in host environment, and design and construction of a board that embeds safe elaboration unit, 2 discrete outputs to the ETCS, just the status like the base option, and an Ethernet interface, master-slave communication, or for the enhanced interface later on.
5 minutes.
What's wrong?
No, you have 5 minutes left, Daniel.
Okay. Wireless also is explored in the real target this year with data coming from the chain, from real chains. This is what has been explored within this year, the class 2 also. Indra was focused essentially on the class 3 since the beginning, implying equipping all wagons with the wireless sensor networks. We can see here another example of the OTI dashboard with the chain composition and chain integrity. In the next slide, Indra is continuing on developing also one board that integrates different sensors for the integrity and also for additional functionalities like diagnosis of cargo and wagon. Simulation activities has been also important from SAIT that included within the runs simulator the OTI module and is in Shift2Rail 4 continuing to explore the OTI behavior in a couple of real lines with different technologies, different product classes. This performance analysis by this year shall give to the demonstrator important information before going to site testing and anyway for the demonstrator's tuning. Cost benefit analysis is also an important piece of work led by DLR and with the contribution from Deutsche Bahn and the Network Rail. Cost analysis and capacity analysis. For instance, in general, on board need to be equipped before being able to remove the trackside. This is an important reference point to be taken into account. Low density line, like in the Cambrian, where we have a couple of trains per hour, the result is that very relevant cost reduction was observed because also in presence of a fallback, anyway, this is quite big as a cost reduction infrastructure level. Different is the result while looking at the high density situations, like for instance in the Offenburg-Fribourg line and the south of Germany, or even in the West Coast main line. The result in this case, there is still some reduction in the cost. Anyway, in general, the bigger benefit in this case is enabling the moving blocks and enabling a further increase in the capacity. In a glance, train length, the topic was added essentially 1 year ago, not originally planned, starting from July in collaboration again with moving blocks. All the deliverables has been updated or are under their review phase. Specifications are already available on the web. Main topic was to design, to implement this, to specify this functionality in a way to be hosted within one same equipment, not having two separate devices, but one single device, suitable to deliver integrity and train length. CBA shall arrive by April, in line with the extended duration of the Shift2Rail 2. Okay, then we can go to the final recap to stay on time. Okay, quick recap. In a few words, results until now has been a big important specification work, functional interface, testing level also, and a formal validation. We have also preliminary results from the cost benefit analysis that shall continue also in Shift2Rail 4, and demonstrators, TRL4 demonstrators under completion by this year in Shift2Rail 4. Activities shall continue, shall be extended safety analysis, performance analysis, as I quoted earlier, site testing, and in the end, formulating a standardization proposal. In a few words, the future impact, potentially future impact in the future, we have seen in a few words, low density line, the cost reduction is quite important and visible. In the high density line, the best result is enabling moving blocks, so enabling a potential increase of the capacity. This is the overall picture, to stay within the 5 minutes warning from Lea. That's all from my side, that's all. And thanks to the team, the partners that contributed to this work, and also to the moving blocks and adaptable communication teams that collaborated with the China integrity team. Okay, question time.
Thank you very much, Danilo, for this presentation. Indeed, you're finishing right on time. So we already have a few questions in the Q&A, so I will start with those. Then I will look to see whether anyone wants to actually ask a question already. So we have a first question from Daniele Trentini, who's asking what are the seal values for the prototype. So the safety integrity values for the prototypes.
The seal is a hot topic since the beginning. Now also Shift2Rail 4 is evaluating, this is an anticipation at least. For sure, OTI as a system level is a SIL4 functionality. An initiative within the TD is exploring the feasibility of having OTI as a SIL2. This is still a topic under consolidation in Shift2Rail 4, so it is at least an anticipation. The deliverable, including this safety analysis, shall be issued by end of this year. I can say, for instance, Hitachi Demonstrator is looking since the beginning to a SIL4 prototype, but anyway, SIL2 seems to be possible, and this is the point under exploration now in Shift2Rail 4.
Okay, clear. Thank you for this answer. I hope it satisfies the person who asked it. And then we have a question from an anonymous attendee who's asking, and maybe there Ulrich will need to bring to be back in the discussion. He's asking, how does the team's work align with the HC and the 3 GPP's train integrity use case? What sort of timescale for deployment is there for teams? That's the second question. So, Danilo,
are we talking about adaptable communication? So in general,
I think it's talking about the use case for teams in the drafting, I guess, of the 5G specification. This is how I understand it, at least.
In general, what we are doing in many cases, at least a couple of demonstrators are doing it. Hitachi and Mermec, for instance, are using the ACS gateway as it is, which means a multi-bearer for the OTI system using this radio. This is fully transparent. This is how the ACS gateway has been designed. So when the 5G shall be available, it shall be part of the bearer that can be used in a transparent way for the master-slave communication. So this is implicitly included in the ACS gateway.
Okay, and what about the timing for the deployment of teams?
Okay, the project is going to complete its work by a couple of years, which includes also site testing. In general, in the next 2 years, we also have one deliverable that includes OTI strategy migration. So we shall explore in detail which is the migration. So up to now, prototyping work, safety analysis. Later on, in our package lead by DLR, we shall have also this kind of information. Not yet now, but we shall have this in the next deliverables, Shift2Rail 4.
Okay, and we have the time for one last question. I see there is one that was that's not answered yet from Alberto Mandler. What is the drawback of the wired solution that justify going to more complex wireless solution? Yes, this is a question indeed that is quite relevant for a lot of people.
In general, 3 different product classes has been defined for different situations. When the Ethernet, for instance, or wired link is available, for sure, this is the appropriate solution. Other solution has been explored as required by the grant agreement. When wired link is not available, this is the reason for exploring also radio interfaces, which, yes, for sure implies higher complexity. So it is just a matter of covering all the possible cases. When the wire is not available, we're talking about existing trains or freight mixed trains. This is the reason.
Clear, thanks a lot. That's it for the questions. I don't see any other question except for a comment related to the DAC delivery program, so the digital autocoupler delivery program. where the user Amazon says, as just a general comment, that the industry is starting to work on it, and this is true. There is a program that's been launched under the coordination of Shift2Rail, and I guess Danilo can also confirm that in the next few weeks and few months, the teams group inside IP2, inside Shift2Rail, will also collaborate with the experts that are going to be involved in this DAC delivery program.
Yes, this topic was recently discussed in the meetings of the project, and Deutsche Bahn shall help us in contacting the DAC project, that is a German initiative to evaluate how to fully integrate this new generation mechanical coupler, automatic mechanical coupler with the train integrity. That shall be an important simplification, for instance, in the class 3. So for sure, this is the next step we have in mind. With the help of the Deutsche Bahn.
Perfect. Thank you very much, Danilo. In the same way, a big thanks to the entire team working with you on this. And it is now time to move to the next presentation. When we are now. We just finished, we just went through, sorry, the presentation of 3 key TDs that will contribute in the next few months and the next few years to enhancing the ETCS ERTMS specifications, and they are so-called ERTMS game changers. IP2 is a key contributor in this respect, but this is not only our activities, we also have other areas of interest and of work. The next one, zero on-site testing, which will be presented by Burkhard Bonner from Thales, is a key one when we are discussing reducing lifecycle cost, improving and accelerating certification processes, and in fine authorization processes. And Burkhard will present to us right now the activities ongoing inside Shift2Rail for the setting up and the creation of a common test laboratory framework. Burkhard, you should be, I will give you the control and you should be able to start presenting.
Okay, I will start with my presentation. Lea, it's forbidden for me to take over the control. Can I have the control?
You should have the control now.
No, I can't share my screen.
Okay, it's fine. Don't worry. I'll do it for you.
Do I have it?
Can you see the screen, Burkhard?
I can see a screen, yes, but I have no control.
It's okay. I will do it for you.
Okay, so yes, what was the initial goal of zero on-site testing? We have in the world various equipment of trackside and onboard, which must be tested in collaboration. And this is the first experience with such field tests takes 5 to 10 times more time compared with testing in the lab. And this is a situation where we can reduce the costs if we transport the test from the field into the lab. That means that we have to elaborate harmonization and standardization of interfaces between the systems under test, and we have also to harmonize procedures for verification and validation of the components. So next slide, please. Yes. What we have done in the past, it was starting in Shift2Rail 1 with an analysis of a status what we have in the world. We have compared it with other industries like automotive sector, and we have defined a common agreed test architecture and a common agreed framework for testing for the process. This was the outcome of Shift2Rail 1. Then we have started in Shift2Rail 3 with the definition of architecture. Then we have developed some interfaces where we have a form-fit functional interface specification for some components what we have to test. Then we have seen that it's necessary to have a common data model, especially for the truck layout of train interface, train infrastructure, and we have developed a method to test these data for formal methods, that they are complete and consistent. At the moment, we are in the phase of implementing some prototypes that we have decided, and we are in the phase of testing these prototypes. What we can do in the future is that we can see we have to share our experience also with other working packages like ATO or moving block or something like that. This will be a challenge also for zero on-site testing in the future. What I mean is it's maybe a task what we can plan for Shift2Rail 5. We can go to the next. Okay, what we have seen, what is necessary. We can see that we have in the middle, that is a little bit darker, we have onboard units, we have RBCs, we have interlockings that are have to cooperate in a test. We can do it in labs by manual interactions, but it is better to have a test environment with controllers for all these components. Where we have such an adapter concept, what we already have developed in UNISIG is an adapter concept between a test control environment and an onboard unit. This is the subset 111-2. We have also the subset 111-3 for an RBC. These subsets we are using in our current test environment. We have different possibilities to combine the test labs and the test environments. What we have written here is a lab A, lab B, lab C, lab D, which can be located in different countries, in different companies. They must be connected via network interfaces, and this we will do in some prototypes. The first prototype is we can see in the next slide, please. So, yes, this is the first prototype where we go to check what we can do with communication between onboard unit and RBC. This is a radio-based adapter, like it is also a part of adaptable communication. system where we have to look for some saboteur actions for that interface. So we have to have possibilities to have delaying messages for corruption of messages, failures, missing messages, destroyed messages, wrong sequence, something like that. In that prototype, we have a controller. It's an RBS controller in the test environment, which can configure the saboteur, what he has to do, and the saboteur will have access like a man in the middle in the radio communication between onboard unit and RBC. So this is one architecture. This is currently under test. So in the next slide, please go to the next slides. It's a little bit complicated here to explain. Next slide, please. Here we can see some screens of it, demonstrators. Left is the test environment, onboard unit, DMI. On the right side, we have a DMI of a train itself. And we have other screens from saboteur, from radio-based system, something like that. So next slide, please. So this is the next configuration, what we have prepared. We are currently under test. We have a test environment located in Germany. It's located in Thales Lab. We have a Lab B. It's an RBC from Hitachi, located in Italy, and we have a Lab C. It's an onboard unit located in Mermek. And what we have to prove here is the concept of UNISIC, that we can work in distributed labs, and we will use here the subset 111-2 and 111-2 specification from UNISIC over distributed labs, establishing a VPN connection between all these labs and to perform some tests to share possibilities. In the next slide, we will have a much more complicated figure. This is because we have in the field, if we look into a corridor concept inside Europe, that we have trackside supplier, we have onboard supplier, and in the network infrastructure, it must be tested that a train can move through a whole corridor.
I think we lost Burkhard. So I think we're having a technical problem with Burkhard. I don't know whether it's a connection issue, and he should be joining us again.
Mm-hmm.
Ah, you're here. Sorry, we lost you for a few seconds here.
Okay. So, okay. This is the current situation, and for we have prepared some little movies about. We can go to the next slide first. Yes. What we have also prepared as a prototype is that we have the situation that some components will have no test interfaces or electronical or software test interfaces where we have to use, for example, the real touch screen of an onboard unit, and where we have to use some robots to perform the actions as done originally by the train driver. And for that, we have to demonstrate that through a test environment and through an onboard unit adapter, this robot can be stimulated to do some actions. So, and in the next slide, I will explain a little bit. It's really the end. I think we have not the latest version of the slides.
Okay.
There, can I take over the screen?
Yes, I will give you the right.
Mm-hmm. Okay.
You have the right now.
Yes, and so yes. What I can show in the first video, you can see it.
Yes, maybe you want to put in full screen. Yeah.
Yes. Yes. Hopefully, yes. Yeah.
It's
okay.
Perfect.
Yes. That we have prepared the train handover from one test environment to another train environment. What we can see here on this slide, that we have two different RBC areas, each controlled by a different test environment. And what we have defined in that interface between two test environments, that we have a special element. It's a virtual element in the truck layout. It's called handover element, which must be known in each truck layout by a unique identification, and this can be used. And in the right screen, we can see here already created train. The train will start its start of mission with a RBC, and then the train starts with moving, crossing some balises in front of that signal. Then he starts performing the RBC handover to another RBC, which is located on the left side here. And what we can see in the movie, that also parallel to the NRBC handover, also the TCLs or the test environments will perform these handover of one train to another test environment. So what we can see, let's a little bit explain it in detail, but because it's not visible very convenient, is that we have a display of a train DMI, where we can see how many connections to RBC the train has currently, and in the video, we will start with a start of mission procedure. Means what we can see on the right side is to enter train data and perform a start of mission procedure. Now I will start with a movie.
You have 5 minutes left, a little bit less.
Yes, okay. So what we can see here is on the left side the screen of a DMI. Now the start of mission is performed, and the train has connected to the RBC and starts with moving. We can see it on the right side that this little worm here is moving in direction of a neighbor RBC. It is passing these balises which contain the session information for the second RBC, for the neighbor, when it starts with connecting the second RBC, and this is currently done. It has an on-site movement of authority, and now it has connection to both RBCs, and now we make a little switch to the neighbor test environment, where we have here this common handover element, and now based on information exchange between both test environment, this train appears here and can be controlled by this test environment completely. So I will stop it here and go back to my to a second movie. Which demonstrates not. It will not work here.
Maybe we can skip over the presentation.
Yes.
Yeah.
Yes. It does not work here. It was only to demonstrate how this roboter is working. Hopefully I can start it. No. So you can see it?
Yes.
But I'm not. Okay. Where you can see how this roboter is working. It acts as a finger of a driver and performs the start of mission activities, means entering the driver ID, when starting with, now he confirms it, chooses the level and confirms the level, what he wants, and now he has to enter RBC contact data, something like that. And okay, I can stop this video here, and I'm ready with my presentation. Thank you.
Thank you very much, Burkhard. I will take over the sharing of our screen.
Yes.
Up. Thank you very much for this. We also still within timing, so that's good. Opening for possible questions from the audience, so either via the Q&A function, which you can use directly via Zoom, or if you feel adventurous, no one has done it yet, you can also ask a question orally and we will open the mic for you. So in the Q&A for the moment, there is no question specifically for you, Burkhard. I will give a few seconds maybe to everyone to ask questions. We have a first one here from an anonymous attendee. Could we quickly see the network diagram, the connections between the lab sites? I guess you want us to go back to the presentation. I will try to find the right diagram for you. I don't know whether you had one in particular in mind, I guess. This one, I guess. You said around slide 134.
Mm-hmm. Yes.
So I guess this attendee wanted to see this slide again. I don't know whether a question will come out of it, I hope. Otherwise, shout out to the others. If you have a question, now it's the time. There are no hands raised for the moment. You wanted a screenshot. Okay, you're welcome. In any case, all the presentations, I assume, will be made available on our website in the next few days. So you don't need to screenshot every slide. All of the presentations will be made available. Before we move to the next presentation, and since Burkhard is still with us, any question regarding the activities on zero on-site testing, or even specifically the two videos that Burkhard has shown? I guess everything was clear. This is good. This is very good. Thanks a lot, Burkhard.
Okay.
Thanks a lot. Still monitoring in the next few seconds the Q&A, but I guess there is no question for you.
Okay.
Thanks a lot. Before the coffee break, we're still going to squeeze in a presentation from Arne Bohal from Trafikverket. And this time around, we're going to dive into the world of formal methods and how those formal methods can actually be applied to railways and simplify the life of railway companies and anyone involved specifically in the making of specifications. Arne, you're here, you're ready?
Yes, I'm ready. Can you hear me?
Yes.
Very
just
good.
give you the control, you should be able to take over from now.
Great, thank you. So good afternoon, everyone. Let me see if I can flip the slide. Yes. So I'm the deputy of this TD 2.7, which is working on formal methods and standardization for signaling systems. Oops. And the overall challenge that we try to address in this TD is the challenge to ensure correct behavior, interoperability, safety, and reliability for signaling systems. And this is illustrated to the right with a process starting with a tender, development and adaptations of, let's say, primarily software-based systems, followed by verification and validation activities aiming to approve systems before they enter revenue service. And this challenge is manifested by schedules being longer than desired and sometimes unpredictable. Errors and omissions can be found late. Delivery may not be as fast as one wants to, and cost increase do take place. There's also other aspects like vendor lock-in, and systems are in general costly to procure, develop, and maintain. And this challenge is, let's see, is quite real, as illustrated on this slide. This is just an example for an ERTMS pilot line where the graph shows software errors that have been detected in wayside systems, where new installations of software over a period of time exhibit, let's say, a peak of errors after commissioning. And of course, the trend is downward, so errors get removed. But still, it serves to illustrate that these software-based systems are complex and they require iterations to mature. And there are some root causes. So this slide illustrates 3 main root causes. The first one is that the tender requirements tend to be imprecise, and this leads to work involved to interpret them, and may lead to design choices that whose impact is not really well understood until later phases. And this might lead to this aspect of vendor lock-in. A second root cause is the use of mainly traditional verification methods like review and test. These take time, and they're mainly good at detecting issues, not proving the absence of issues. And having these vague and imprecise requirements to start with complicates this further. The third root cause is that there's a lack of standard system architecture with standard interfaces. So if you have systems from different generations and different vendors, you may need to multiply effort, or effort becomes duplicated for different kinds of systems. And this, of course, has a negative impact that it prevents or limits reuse, plug and play concepts, or off-the-shelf components. So the objective of RTD is to use formal methods and standard interfaces to address these, to address this challenge and the root causes, and specifically trying to use formal methods to meet the customer demand on modular interoperable systems with standard interfaces, and able to verify compliance to customer requirements using formal methods, including verification of safety of these systems. So we're concerned with the processes and the interfaces in the evolution phases of signaling systems related to design, implementation, and so forth. So our work has been carried out in 2 phases in Shift2Rail 2. The first phase classified what kind of formal methods are out there, what can be used. And this included definition of a number of formal methods use cases. So these are describing relevant applications of formal methods in railway signaling. And this phase also selected case studies that we have performed and the approach to standard interfaces. And these case studies, they were performed in phase 2, which we're about to finalize now and in the next couple of months. And the objective of these case study applications was to evaluate the benefits that can be achieved thanks to formal methods and standard interfaces. In parallel with this, we have a business case task which aims to produce a business case for formal methods and standard interfaces. So in the first phase, we had a main document deliverable, which is, so this is not the latest version of the slides I see now, but that doesn't matter much. This deliverable D51, this describes the different formal methods that exist, classifies them, and captures the specific tools and methods that are available, and is really aimed to railway engineers and signaling managers, and also describing these formal methods use cases I mentioned. It also describes how formal methods relate to the commonly known lifecycle phases of the Senelec standards that apply for railway signaling. It describes representative success stories of formal methods in railways. It accounts for surveys that we have done on industry expectations on formal methods, what can be learned, and aspects of importance to gain the benefits of formal methods. And the classification of formal methods is illustrated on this slide. There are 4 different kinds, basically. The first one is formal specification, illustrated to the right. An engineer thinks of something, writes it down in pure English, and to the right, there's some formal specification of some intent that's being expressed in a precise and unambiguous way. So formal specification is about formalizing system requirements. The second kind is formal verification. So in that technique, you take a formal requirement and some formal model, and you use a software tool to verify if this requirement is satisfied by the model. If it is, you have established a mathematical proof, and if it's not, you can inspect why this is not the case by looking at the debug trace, basically a test case showing why the property is not satisfied. The third category is formal development. Formal development, as the name implies, is really a tool-supported process to develop software, basically, that includes the use of both formal specification and formal verification, and possibly also many other techniques to aid to develop software-based systems that can be described and verified using formal methods. The fourth category is special purpose, and one can think of this as an app. Everything is an app, and you can use formal specification and formal verification, for instance, and package a formal app that does something simpler, maybe solves a very specific task, verifying some built-in properties connected to some application so that you can get the benefits without having to do any manual work. From our phase 1, we have some conclusions, and the first one is that there's no standard formal method or tool that meets all needs for all applications. There are many different methods, and some of them require a lot of understanding of how to use, and some of them don't. But what we have found in phase 1 are these formal methods use cases that are a little bit independent of individual methods and tools. We note that formal methods are highly recommended by standards. They are prescribed by some organizations, and they are actively used in the railway industry. Some examples are, of course, that infrastructure managers, several of them, prescribe the use of formal verification for safety. This includes Trafikverket, SNCF, subway operators in New York, Paris, and Stockholm. And several suppliers use formal methods in-house and have such expertise. And yeah, I'll go on. So in phase 2, we performed 2 case studies, and together they cover all the formal methods use cases I mentioned earlier. The 2 case studies are for slightly different purpose. The first one is related to using formal methods in the process to create and define a standard interface. And this was a case study based on the EU links methodology. 2 formal methods use cases were applied. The first is development of systems with standard interfaces using semi-formal methods together with test case generation. In the second case study, formal methods were used in development and V&V of software for a subsystem, a level crossing subsystem that uses a standard interface. And this included 4 different formal methods use cases. I'll come back to the specifics about each case study. So the first case study aimed to introduce formal methods into the model-based system engineering approach that's used in the EU Links project to define standard interfaces. There were 2 EU Links interfaces selected, one related to a level crossing and another to a point. And the purpose of this was to improve how system requirements and specifications were created and analyzed. And the formal methods that were applied were based on the semi-formal SysML modeling that takes place in EU Links. So the first step was to create a formal model of those interfaces in order to be able to verify, using formal verification, consistency requirements, such as absence of deadlocks, and also user-supplied safety properties. The third task was to automate test case generation from these behavioral specifications in order to come up with standard test suites. Looking at this case study using the V cycle, it's illustrated here as the top left part of the bigger V, where the so coming up with the standard definition of a standard interface. In this context, state machines are used to implement the behavior expressed by the infrastructure managers, starting off with domain knowledge, sequence diagrams, down to a state machine implementation, which is then tested and verified to be accepted as the behavior desired. The test case generation was applied by creating a dedicated model for test case generation from the EU Links specifications. This was rather straightforward, as there are similar in language that's used to express the models. And what one can note here is that testing is maybe not a formal method per se, but in this case, formal methods are used by the software tools for test case generation. So they use formal verification techniques in order to generate test suites that cover coverage objectives of the model. And
5 minutes left.
Oh, 5 minutes only?
Yes.
Really?
Yes, time flies. Go
I
ahead.
thought okay, wow. Okay, so the purpose here was to generate test cases to improve quality of specifications. I go on, and the achievements here in the case study 1 were to perform these formal methods applications, including formalization and test case generation, and it led to issues that were detected in the specifications studied, which have become integrated. What can be observed from case study 1 is that the quality of interface specifications matter. The modeling language needs to be clear and unambiguous. This goes into the semi-formal semantics nature. Common encoding and modeling challenges should really be automated in the future. It was noted that safety requirements were not part of the EU Links approach from the start, so this is something to address in the future, perhaps. There is potential to create a formal app to verify consistency requirements. And when it comes to test case generation, this was rather unproblematic to do and can be used to standardize test suites. The second case study aimed to use formal methods as part of the software development of system implementations. And in order to tackle the root causes of the challenge I mentioned initially. It was applied to a small but real level crossing system based on a tender by Trafikverket, the Swedish Transport Administration. And it included several use cases. Tender-based safety verification, which is focused on verifying safety of implementations. Formal verification of configuration data, which is a formal app, if you will. Formal development, where several approaches to formal development were applied in parallel with a traditional software development approach. And finally, a V&V phase where test case generation and formal verification of safety took place. And as part of this study, this first phase, the tender requirements were elaborated into a common architectural basis. This served as basis for the formal verification of configuration data, and also served as an architectural design for the different implementations of software to formalize safety requirements and test case generation. This slide just illustrates the safety verification. So based on safety requirements, different implementations models were made subject to formal verification of the safety conditions. And safety verification found real issues using formal verification. It was possible to re-verify updated implementations. And it was noted that if you do formal verification of safety requirements already during development, this helps. And it's possible to have 0 deviations. But we also found issues in the safety requirements themselves during this process, which goes to show that requirements need to be validated to be mature. So lessons learned is that, as you can expect, a predefined methodology for formal development is useful. Techniques with simulation and formal verification being used as part of the development are beneficial for quality of results. This is an illustration of one of the tracks where visualization in a graphical way, this can be useful to spot issues and to be able to converge on the development activities sooner. So the main conclusions from this case study is that tender requirements need to be of a certain quality to enable efficient use of formal methods. A clear natural language basis is important, but even so, you can expect to find issues before you have validated requirements. For this purpose, tender requirements typically need to be further detailed, as was done here with an architectural design that forms the basis for implementations and formalized requirements. And taken together, the objectives that were set out, this case study demonstrated that it's possible to meet these goals on being able to demonstrate compliance to end customer requirements and verify safety using formal verification. Overall, in phase 2, we think we've had a successful collaboration and learning among the members, where application of formal methods for different purposes and different phases in the system lifecycle have been beneficial. We've reached further in common conclusions and recommendations from these 2 demonstrators. And we've gained input for the business case, which is currently being worked on. It should be noted that the results that we have achieved in Shift2Rail 2, they are focused on the subsystem level, whereas in Shift2Rail 5, in the future project, the intent is to move to higher up in the hierarchy, so to speak, to consider also the system of systems level. We expect that further benefits of formal methods could be expected, but also some new challenges.
I suggest that you try to conclude, Arne.
This is maybe my last slide here. So
perfect.
As a final recommendations, we think that formal methods, they are important and they should be used to ensure system properties that are critical. And the reason for this is that the level of trust is significantly higher than traditional V&V. It can be automated, and they provide valuable feedback. And railway is not the only area for formal methods, but railways is very suited for formal methods. That's because the ramps requirements are very high in railways. The concept and principles in railways are well understood and lend themselves very well for formal methods, as evidenced by many success stories that exist. And we think that formal methods have potential for the future to be more widely used. And this is because methods are maturing and computing power has raised, which is important. And we think that formal methods can set the benchmark for how to assess system quality. And this is also evidenced by a growing need and interest for formal methods from the industry in general. So I'll conclude there. Thank you very much.
Thank you very much, Arne, for this presentation. Looking into the Q&A very quickly before we stop for a quick coffee break and to see whether there are questions. For the moment, there is no question in the Q&A. Anyone wants to ask a question on formal methods to Arne? I have one, and I think it's really linked to your last words. It was whether or not you were optimistic about the uptake of formal methods in the rail sector, and whether all the industry players will be ready in the near future to actually start using them.
Yes, I'm optimistic. I mean, if you look at the European landscape, for instance, all the major suppliers, they are using it, and I would believe that they are planning to increase their use rather than the opposite. Of course, I can't speak for them, but this is the impression I get. I have no doubt in my mind that the use of formal methods will increase in Europe, but also elsewhere in the world. Okay.
We have one question in the Q&A, again from anonymous attendee. So he or she says, if I well understand, the safety requirements prone to be also formalized. How can we be sure that the safety requirements are correctly formalized? Like a safety requirements.
Right. Well, I mean, this is a common question, I think. It's just like anything else. You can review it. If you write a requirement, whether it's formal or natural language, you can review it. A benefit of formal methods is that you can actually apply it. So the example with safety requirements and system models, you can also attempt to verify it. And that's one type of validation, which is also useful. As I mentioned in the second case study, we actually found some mistakes in some safety requirements, and this is natural. In a way, it takes a little bit of time for requirements to mature too, just like in the software case I exemplified.
Yeah.
But in general, safety requirements are easier than many other normal kind of requirements, because they can very often be expressed in a more compact form, because you don't necessarily care how safety is accomplished. You can just zero in on describing what the actual safety requirement is.
Clear. Thank you, Arne. I don't see any other question in the Q&A, and I don't see any hands raised from the participant, from the audience. So I suggest that we stop here. We are 10 minutes delayed compared to the official schedule, but it still allows everyone to, 15 minutes delayed, to grab a cup of coffee or tea, water, and we will make a quick break now, and we will resume at 4 on the dot. And we will continue with another 3 presentations this afternoon. One we will follow just after the break on the virtually coupled train sets. It's quite looking forward to see what they have in store for this one. We have a presentation plan on traffic management system and its evolution, and we will finish with a wonderful topic of cyber security for railways. So I invite you to enjoy this quick break, and we'll see you all again at 4 on the same here in the same virtual room. Thank you very much again to the speakers from the first session. Are now getting ready to start the second part of this session dedicated to IP2. As I said, we have 3 presentations left: virtual coupling, traffic management, and cybersecurity. And I'm very happy to welcome Moritz Schenker from DLR, who's part of the virtual coupling technology demonstrator of Shift2Rail, and who will present today to us where the TD stands in terms of achievement in this specific area. Moritz, like others, I will give you the control. You should have it now, and I give you the floor now for the next 20 minutes.
Yes, thank you for the introduction, Leah. I hope everyone can hear me clearly.
It's all good for now. Go ahead.
Perfect. So good afternoon from my side as well. I'd like to welcome you to the short session about virtually coupled train sets and the ongoing developments in our work packages in X2Rail 3. We are part of the technical demonstrator 2.8. And yeah, we just started our work packages a little over 1.5 years ago. So this are really early developments in progress here. But for today's presentation, I want to introduce you to the goals and vision that we have for virtual coupling, and then go a bit more into detail on the system concept that we developed in our first deliverable, D6.1, which is publicly available. Afterwards, I'm going to briefly talk about the performance and safety analysis that we conducted in the second deliverable, which is confidential, and then round out the presentation with a short outlook on our ongoing and next tasks and projects, and of course, some conclusions. Now, when the X2Rail 3 project was established, in the description of action, the partners agreed on the main goals that we want to achieve with virtual coupling. And first and foremost, this is to increase the line capacity by reducing the headway between trains. So we want to contribute to a higher capacity of passenger and freight transportation, and of course also reduce the amount of crowded trains on lines. Besides that, we also aim to increase the operational flexibility by ensuring interoperability between all vehicle types and models. A little smaller, but nonetheless very important point is that we want to contribute to improving the use of existing stations. This really means, for example, for short station platforms, with virtual coupling, we are able to utilize multiple platforms at the same time with one virtually coupled platoon, and in order to maximize the use of this station. Now, last but not least, of course, we also want to help to reduce the overall railway costs by focusing on onboard equipment and electronic systems instead of increasing capacity by adding new tracks or other heavy changes to the infrastructure. Now, with this aim to reduce or to increase the use of existing platforms and lines, we also want to reduce the relative maintenance costs of railway operation. So all of these goals now funnel into the main aim that is also represented in Shift2Rail, of course, to increase the competitiveness of the railway transport sector with respect to other transportation means. Now, in order to visualize the idea of virtual coupling, I want to show a short video which we created at DLR for the InnoTrans in 2016. So this video was already created before the X2Rail 3 project started, but however, it still illustrates nicely many of the main aspects that we are now dealing with in the collaborative work in X2Rail 3. In this video, you can see a scenario with 2 different trains coming from different directions and calling at the same station. Now those trains are bound to be joined behind the station in order to enable virtual coupling. So once these trains enter a common stretch, the one train doesn't have to wait until the other leaves the area. Now, in order to ensure a virtual link between those trains, we of course need multiple components and onboard equipment. The most important thing that we need is accurate measuring, and this really relates to distance measurement, but also relative speed and acceleration measurement. Now here, back then it was illustrated with GNSS, but we are really technology open in our project, and we just need any mean to provide us with an accurate estimate of all those parameters. Now, once two trains are agreed to virtually couple, they will establish the train-to-train communication, which represents the virtual link of those trains during the coupled operation. As you can see here, we will have multiple means of train-to-train communications for different ranges, long, medium, and short, but also to have redundant means and fail-safe communication. The same applies for the other onboard units. Of course, we will have redundant means of distance measurement in order to ensure a fail-safe operation and just a safe head rate control of those trains. Now, once the common stretch of those two trains is over, they will be able to perform on-the-fly maneuvers to decouple and to allow for very efficient and smooth railway operation. Now, this was the idea and the vision that we had coming into the project. And then in the end of 2018, in December, we came together with partners from all over Europe under the lead of Hitachi Rail and started to really materialize these ideas and vision that all of the partners had, and started to develop a collaborative concept together. And this concept is now based on the paradigm change that we call breaking the ball. This means that we want to go from absolute braking distance, which in this graphic is visualized by this wall in the rear end of the front train, to establish a virtual link between two trains and diminish this distance to a relative braking distance. So this means we go from standalone trains with absolute braking distance to a virtually coupled train set with relative braking distance. And what we need for that is a safe platoon and consist management. And this includes many of the components and equipment that we just saw in the video. Of course, we need onboard sensors for the real-time supervision of distance and relative speed and acceleration and so on. But we also need the train-to-train communication to exchange the dynamics and enable the cooperative movement. Last but not least, of course, we need control units to execute safe commands for traction and braking of those trains. Now, the charm of this concept is that to the outside, to the signaling, to the external systems, the virtually coupled platoon is seen as one train with a single unique ID that follows the rules of the underlying signaling system. So of course, here we face new challenges in the operation because now we don't have a train with a fixed length anymore, but we have a platoon that has a variable length, for example, depending on speed and other parameters. And we will also have the gaps in between the trains. However, this concept still allows us to operate, or we want to achieve to operate on any underlying signaling system, as this platoon management is purely done by onboard components and does not very much rely on the trackside equipment. Now, this concept was then fixed in our first deliverable into a functional layer structure. And here we envisaged 4 different layers for services, strategy, tactics, and operation. Now, the higher level layers for services and strategy, they focus on traffic management systems and service providers. But for the first part of our project, we really focused on the implementation of virtual coupling in those bottom layers. So the tactical layer and the operational layer. And the operational layer in this case implements those components that we just seen, the train-to-train communication, the onboard sensors and controls. And this one is the safety critical layer. This layer needs to ensure that the local movements of the trains are safely executed and that the platoon behavior is stable all the time. Now going one layer above to the tactics, here we have the platoon management with an additional degree of freedom. This layer is in charge of coordinating the movement of trains once they enter the platoon until they leave it again, and also has to handle unexpected events and degraded situations, of course. But now on this layer, we are able to implement those efficient and on-the-fly maneuvers, and we have the possibility to optimize our operation within the platoon, for example, with respect to time delays or energy consumption. So there comes the additional degree of freedom. Now, all these functionalities with the onboard or with the on-the-fly maneuvers, of course, cannot be implemented just in one step. It would just disrupt the whole operation as it is now. So what we developed in our first deliverable is a stage concept with a minimum complexity stage 1 that really simplifies the shift of operation in the first step, which is stage 1. Here we want to build on an existing procedure of mechanical coupling, so joining and dividing trains during actual operation, and just replace this mechanical link by our virtual link, the train-to-train communication, and establishing virtual coupled train sets. Now, in order to ensure working operation with this virtually coupled train sets, we divided the tasks that we need to fulfill into 5 main functions. And the first function here is again the safety critical one, to protect the consists inside the platoon from collision. And of course, this layer, which is the operational layer, needs to be implemented in the first stage already to the full extent, as we need to ensure that our system is safe. However, for the next 3 tasks, the coupling setup, the coupled driving itself, and then the termination of coupling, in this first stage, we really want to go to a minimum complexity approach. So we take the existing procedure of mechanical coupling with nearly identical vehicles, so we have really similar dynamics in the trains, and we couple them virtually in standstill and as scheduled by the timetable. So here we avoid any difficulties that we may have with those on-the-fly maneuvers. For the coupled driving, we of course need a basic platoon management and the tactical layer, of course, also in this first stage. Now, this reduced complexity approach allows us to have interaction with the external systems very similar to today's operation. As such, just like in a mechanical coupled train, the communication with the external systems will be done via the lead consists, so the leading train in the platoon, and all the necessary informations will be passed via train-to-train communications within the platoon. The changes that we have is, of course, some changes in the interaction with the interlocking, as we need to make sure that this variable platoon length and the gaps in between the trains are considered well. Now, once this stage is implemented and working, we can start and look further to implement additional functionalities that really show the benefits of virtual coupling. And what we aim for here is the smooth and efficient operation with those on-the-fly maneuvers that I talked about. And to give you some examples here, we can think of starting coupling on the fly, decoupling on the fly, but also introducing unscheduled coupling and decoupling maneuvers, for example, in order to minimize the delay of any degraded timetable situations. So in this case, we need new interactions with the traffic management systems, which then is our interface to the strategic layer. Other maneuvers that we are thinking about is calling at multiple platforms, as I introduced it in the beginning, to really maximize the use of those stations. And here, of course, we also need some new interactions with the interlocking, as we need advanced routing mechanisms in order to make that possible. Now, with this stage approach and the layer concept that we developed in our first deliverable, we went ahead in the second one and looked at what performance we can actually gain with our concept. And one of the main takeaways in our study was that the VCDS has the potential to improve rail operations by combining some aspects that usually contradict each other a bit. So we have capacity, flexibility, and robustness. And if we look at conventional operation and we want to increase capacity just by deploying more trains or utilizing mechanical coupling, we usually lose out a bit on flexibility or robustness. Now with virtual coupling, that does not need to be the case anymore, because we, for example, can deploy shorter and independent units in order to increase our capacity and still gain flexibility with that approach. Now for our deliverable in D6.2, we focused more on the capacity aspect, as this is also a Shift2Rail KPI, key performance indicator. And for this, we conducted several studies. The first of all was to look at just in stage 1, so coupling and standstill, the reduced coupling and decoupling time that we have because of not mechanically coupling anymore, but just establishing the virtual link. And we found that for some of the impact scenarios, we already can have some significant improvements in the capacity just by purely considering this reduced coupling times. Now, what was even more interesting in our research is the results of this paradigm shift from absolute to relative braking distance.
5 minutes left, huh?
Yes, thank you, Leah. In order to understand that, we need first a proper definition, of course, of this relative braking distance. And this is regarded as the distance between trains that guarantees safe braking to standstill. So if one of our first trains initiates an emergency brake or comes to stop, we need to ensure that the rear trains have sufficient distance in order to stop as well. Now, if we look at this distance in an idealized way, so without any delays, with the assumption of 100 precise measurement and control, this distance would be 0. Because once those trains travel at the same time, they could theoretically follow the same braking curve and thus never change the distance. Of course, as you may think, this is not at all the case in reality. We have multiple factors of influence that make our relative braking distance grow and include safety margins. These are, for example, latencies with respect to communication, control, or brake force buildup times, but also inaccuracies in the measurement, inaccuracies in the braking capabilities, or just different braking capabilities in the train, and then also, of course, different speed levels. So we conducted a really detailed analysis in our development, but just to show you, to give you a quick impression on how the relative braking distance compares to the absolute braking distance. I have a preliminary result of calculations for the relative braking distance if we use some assumptions and boundary conditions for target technologies, considering reaction delays, inaccuracies in the measurement, and additional safety margins as well. And we see here for some of the impact scenarios, so high speed, regional, metro, and freight. For the lower 3, the regional, metro, and freight scenarios, we were able to cut down the straightaway calculated absolute braking distance to about 1/3 with our relative braking distance. And for the high speed scenario, even to about 1/5 of the absolute braking distance that we need. So combined with the safety analysis that was conducted in the lead with Hitachi, we can say that given the right technology developments, we are or we will be able to increase the capacity safely by switching from absolute to relative braking distance. And now to give you an outlook on what we are currently working on and what will be our next tasks, we are about to finish the technical feasibility analysis. Here we are dealing with the identification of critical aspects in the implementation of virtual coupling. So we divided our system into multiple subsystems and contacted experts from other Shift2Rail technical demonstrators in order to show them our concepts and identify critical aspects that they see in their respective technologies, and also try to come up with solutions and mitigation measures. In this task, we are also working on a preliminary introduction strategy or migration roadmap. For this, you can see a preliminary illustration here on the right. We divided this into 3 main tasks: the development of the core functions for VCTS, then of course testing and verification with ITRL demonstrators and proof of concept, and then the rollout in the end. Now the next tasks, we just started with the system requirement specification. So here we will actually dive into detail on what is required to achieve virtual coupling and what technologies may be able to provide us with the functions that we need. And then next year we will look ahead and analyze the impact on the whole system. So also on standardization, as our current early work is not yet relevant for the ongoing TSI developments. And then we will finish out with an outlook on the business model for virtual coupling. So to give you the conclusion of today's presentation, I want to recap some of the main points. With virtually coupled train sets, we can help to increase capacity, flexibility, and robustness of a line without major infrastructural changes, as we want to introduce decreased headway between trains and reduce the coupling times when compared to mechanical coupling. We want to make the rail operation more efficient and dynamic by introducing on-the-fly maneuvers, and we aim to achieve interoperability by coupling between any train types and models. Now, this is possible with the right system designs and control mechanisms in place. And I want to stress again that our system is not tailored to a signaling system, so we are rather independent. We are not introducing any new barriers to railway operation, and thus we are fully compatible with the aim of a single European rail area. So to conclude, virtual coupling can help to increase the competitiveness with respect to other transportation means as we enable more efficient freight and passenger transportation. And this leaves me to say thank you for your attention. I think I don't have the controlling. Oh, yeah. And I'm very much looking forward to your questions and discussion. Thank you.
Thank you very much, Moritz. That was very interesting. I see that there was already, I think, a mini exchange in the chat while you were presenting. Okay. Between Peter Mim and I think Michael Mayer-Suhester answered him. I will maybe quickly go to this. I think Peter Mim had a comment referring to the the accident that happened, I think, 20 years ago in Germany, where an ICE train crashed against the bridge, and question of Peter was that with the virtual coupling, whether the second train set would actually also have crashed due to the braking distance that will be reduced between the two trains. I don't know whether you want to comment on that, Moritz. Michael has answered that a difference may not be that big. I don't know whether you have follow-up comments on that.
Yeah, this is of course an interesting point and also a critical point that needs to be addressed. But I think that overall, our aim should be to control the railway operation in a way that derailment is prevented, of course. And this is very hard to quantify the differences in our approach when you compare it, for example, to, as Michael Mayer-Suhester said, a mechanically coupled train set in that regard, as the impact might be different.
Okay. We have a question in the Q&A box from Ludovic Sedou, who is asking, did you think to couple more than two trains? In case of major network incident, I will think it could help to quicker the flow, recovery of the flow, recovery of the operations.
Of course, yeah, we are thinking about that now. My graphics in the presentations were all with just two trains, but of course our concept is also aiming to couple more than two trains in order to make sure we have an even more efficient operation. The thing here is that probably just two trains will couple at once, and then the third train will couple to this already established platoon, so we don't have any chaos in the coupling procedures. But yeah, this is something we think about for sure.
Okay, clear. Thank you. We have another question. Could you speak, from Miguel Llegas, could you speak about what could be the strategy during the coupling maneuver? Will the master train command also the slave train?
Yeah, thank you for that question. It is not foreseen that the master train one-to-one just commands the second train, so the slave train, as you said, but rather they exchange their dynamics, and the second train is in a kind of automatic way approaching the first train, but not as a remote control from the master train, but yeah, in an automated way.
Okay, thank you. Any other question before we move to the next presentation? It is now or never. I see that no one has raised the hand either, and I see nothing new coming into the Q&A. I leave it a few seconds. No, I guess that was it, but there were already interesting questions. Thanks a lot, Mohit, and also thanks to the entire team of the Technology Demonstrator, who's working hard on this. And thank you again for your presentation today. Thank you.
Thank you, Leah.
We're moving to the next and not the least, traffic management system. We have the TD leader of the activity inside IP2, Roland Kuhn from Bombardier, who's ready to go, I believe. I see him. And he will present to you the current stages of the work on traffic management and the evolution that the team is planning for the near future, hopefully. Roland, can you hear me?
Yeah, I can hear you. Hello, Leah.
Hello. I give you the control, so you should be able to go through the slides yourself from, yeah, perfect.
Okay, works. Okay, hello to everyone around this webinar. My name is Roland Kuhn. I'm from Bombardier, and I'm currently in charge of the TD 2.9 traffic management evolution, and also in the CCA, the so-called work area integrated mobility, which is a branch of the traffic management evolution, specifically dedicated to freight operations. So this is skip. Okay. Yes, within the traffic management works, this started around 2015. We had a pilot project ahead, and here we laid the complete feasibility foundation, requirement gathering, and so on for our later work. So based on this work, the project was called Shift2Rail. Perhaps some of you remember it. We have addressed 4 innovation areas for the future evolution of the traffic management. So the first one is the integration. So if you go now in an existing implementation around the world, you see a lot of fragmentized installations which cannot send data, exchange data between each other. Sometimes they still use paperwork and so on. So this was quite obviously in the beginning that we need a one for all communication platform, including the interfaces, the application programming interfaces. The second thing, what we also saw was with every application, you have a different workstation. So you cannot switch applications to be on the same workstations like you have at home with your laptop. You can switch between Excel, PowerPoint, Word, and so on. This was largely not possible with the given implementation. And the latest thing was we wanted to achieve something like you had the feeling with plug and play, one of the slogans which you have on the modern iPhones. So we developed the idea to specify an application framework which is suitable for rail applications. Being aware that there are multiple products on the market, and therefore we did only the specification like a kind of a golden requirement specs, which you can use to select amongst the components of the shelf. Another part which we wanted to address is automation. So we will provide, or we are providing with the new setup, a continuous update on status changes of your resources and assets involved in the traffic operations, which helps you with some new application to do a much better forecast of the traffic status. And also, if you are using this information within a maintenance service organization, you can better plan let's say, availability of slots when you do want to do your maintenance and so on. And the second thing is the plus of data received shall deliver a higher quality of the decision processes. This means all the traffic management decisions somehow, if they cannot be automated and you have to make a decision between scenario 1 or scenario 2, then if you have more data, then your decision is more accurate and probably also leads to better results. The third part, what we want to look at is we want to specify and develop new applications or upgrade applications or develop new features for existing applications. I have mentioned only a few because the box in the slide was rather small. So what we are developing demonstrators for an wayside ATO. We have several demonstrators which are addressing traffic regulation, and also we have demonstrators which are related to disposition decisions, what I mentioned according to the availability of the resources. And last but not least, what we need to achieve is standardization. So one prerequisite, and this is really mandatory in the future, if we want to integrate our rail services, we need one conceptual data model, the abbreviation is CDM, which comprised all data which need to be exchanged in a structured way so that everyone who is subscribed to the communication platform and reads the data knows exactly what the data means. So if you look now at the landscape of data models, you find a lot of them. This was of the things also we discussed it very early. There we decided to start the definition of such a conceptual data model. Last but not least, for standardization, we have the APIs. So we are specifying the interfaces. We have done a few already. They are publicly available and will help you if somebody wants to start the development of such a product. Okay. Yeah, a few details. The communication platform, our working name is the integration layer. It's a system, a communication system, which links all the different rail services. We use high-speed data transmission. We have chosen the in-memory data grid technology as we are using a data-centric approach, and the in-memory data grid supports this the best. Here also we did within the works analysis of our components off the shelf. There are different brands available. Some are suited better for messaging purposes. Some are better for data management purposes. We have done a specification which defines the minimum requirements, and you can look what is available on the market. So we are specifying standardized interfaces. We have done a specification for one web interface, and what is important, all data which will be broadcasted via the integration layer will follow the conceptual data model. So at the lower end here with my cursor, you see we have done deliverables. By the way, the Shift2Rail 2 work package 6 is finished. Since February this year, we are currently working in Shift2Rail 4, work package 8, 9, and 10, where we mainly build the demonstrators up to TRL 6 and further define in more depth some application and use cases. Coming to the second part, okay, application framework. Again here, as mentioned already, there are already systems available on the market. You can select. What we did is to specify the minimum requirements for the to be used in rail business, and yeah, they help you in that sense that they automate and standardize certain non-functional processes. So you have a better feeling of a plug and play implementation if you want to implement new applications into your system. Also here we have already a deliverable. This is a system requirement specification for such application framework, which helps you to select a suitable product. Then we have the operator's workstation, as already said. If we have one integration layer comprising all the different information, we also need operator workstation, which have a multi-application and a multi-user feature, and also which includes some specific focus on human factors. So the second thing was we cannot ask the client to throw away everything. So this concept needs to offer a migration path to integrate legacy and new applications. And last but not least, the specification of these operator workstations, which you also may find some available products already on the market, shall follow the TMS requirements. Also here we have one delivery already available publicly. This is the system requirement specification for standardized operator workstation. So this is, I do not want to go into so much detail because otherwise I need more time than I have. So the blue bar in the middle is the integration layer, the data highway. So you see we are connecting different services from the integration layer. We are different services applications. Here in the sample, I showed the traffic control and the timetable management. On the other side, via the API, you connect to the field. So we have the traffic control parts, RBC, interlocking, and in the future we will have also the ATO client communicating with the integration layer. Then we have interfaces for services and other clients, and on the right-hand side, you see we are using the web interface in a moment to get external information, especially weather information in which we need in the future also for the ATO operation. So this is a short diagram about the integration of application framework with the integration layer. I think I said already, so you can select commercial systems and what an application framework does for you. It standardizes for you a lot of function. I shown here a few deployment of software, monitoring of the status of the software, start, stop, failover, and removal, just the most known processes. The workstation. So what we decided to propose is to use a workspace manager. So if you use a workspace manager, we start at the left side. You have the client number 2. It is a very special application which requires its own workstation. You will still have it also with the integration layer, but you can do a little, the lowest level of integration via the integration layer. So this is the first part of the migration. Then the workspace manager, where you also can have different products off the shelf. You can either design new applications, this is application D, where also the user interface and everything is included, or you have an existing application where you need to define a small application to be included into the workspace manager. And the other part is the standard operator workstation operating system. So the workspace manager would provide you with some functionality of a unified user interface. So you can do dashboard management like you can do on your laptop already. You have a unified, normally you have unified toolbar, which can be used by the plugins. This gives you a better same look and feel of all the applications. And oh, sorry. Yeah, next one. So, no, this was up. Okay, down. Sorry. So the automation. So as already said, we are looking very much to use the component of the shelf. Middleware for the high-speed data transmission. Also, as already mentioned, the in-memory data grid solutions are available. Here we refer to one deliverable where we did also the most of the evaluation of the products. This is Shift2Rail deliverable 8.3, which is also publicly available. And the general approach already mentioned is subscribe and publish methodology, not a point-to-point, so that all the clients subscribed can read directly and simultaneously all the updates of the status changes of the resources. So what's
5
also
minutes left, hold on.
Oh yeah.
Yeah.
What's also left, what's also coming with it is we are looking to use a sandbox methodology. So, for example, if you have to discuss with certain stakeholders, let's say a revised timetable, and you need to make some modeling. You can send this, it looks like a real timetable, but it's encapsulated in a sandbox. You can send this back and forth, make modifications without impacting the operational timetable, the production timetable. And if you have all partners agreed, then you can switch it and you replace the operational timetable with this part, which is encapsulated in the sandbox. So applications, very quick. So we are doing also a lot of demonstrators with new applications. I've tried to group it a little bit. So we have, we can sort it in mission domain operations. We we have some for infrastructure, which affecting the infrastructure, and some which are affecting the administrative domains. As you will receive, I guess, these slides, so I will not go to each of them. But just to mention the targets, so we wanted to achieve improved reliability. We wanted to reduce, if possible, the delays, increase the level of automation, and maximizing the level of digitization. This was one of the main targets what we have. And you can find all these use cases in the deliverable D6.3 of the work package 6 of Shift2Rail 2. So last slide. I did this slide just to show how linked everything is. So we started with the part in the middle, the Shift2Rail, where we had a combination out of asset management parts, TMS parts, TMS requirements. Then coming with the Shift2Rail projects, it diverged into the IP2, where it's more technically oriented, TMS, and the Impact 2 with the follow project Find2, where it's where we develop freight specific solutions. On the other side, you see on the left side, the links for rail. They are key for us because they develop the conceptual data model. We are linked with into Smart IP3 because we need from them the asset status evaluation, meaning let's get availability vector with some plus and minus values. So you can use some smart algorithms inside the TMS to see whether you still can use the asset or if you have to do already a speed restriction or a weight reduction if it is concerned about a switch. And we have also other parts in IP4, which is coming in Shift2Rail 5, in cohesive, which starts in December, most probably, where we link the crowd management with some information transfer into the TMS to also to improve further the decisions. So that's my part. I hope I'm in time. It was really fast, Leah. So yes, thanks for your patience and that you listened. And I'm really keen to see your questions. Thank you.
Thank you very much, Roland, for this. Yes, it was very fast, but you were right in the timing. So thank you for this. Again, like for previous session, I'm opening for Q&A. I see there is already one question, but I encourage everyone to ask questions if you have any. I see that no one is raising hands. The one question that is already in the Q&A is from Christophe Chéron, who I think anticipated your last slide by asking what are the connections of the CDM work inside IEP2 with the CDM activities ongoing in Links4Rail. And I think
I can answer this quickly. So we are defining from the TMS which data needs to be exchanged between the services with a TMS view. So this is the deliverable D6.1, and now we wait that Links4Rail is finalizing the rules for the conceptual data model, and then we generate the code which we need according to this model, according to the structure, whatever comes out to be used in our implementation. So we are then, let's say, called a user of the model developed in Links4Rail. And also the other IPs and other work packages, they are in the same situation. So I guess that, or I assume that the model developed in Links4Rail, the CDM, will be applicable then for all projects in Shift2Rail.
Yeah, this is indeed the objective by creating
Yes.
this overarching project that Links4Rail provides input and provides the link across the different innovation program in Shift2Rail.
Yes.
So I hope this answers your question, Christophe. We have another question from an anonymous attendee. Given the interdependency, on other areas, example CDM, do you have an approximate time scale?
Okay, so I'm looking forward to provide to the Links4Rail the data needed for the TMS. So if other parts of Shift2Rail are also interested to use the CDM, they also need to create a work package or whatever position, and then it can be discussed in the Links2Rail, let's say for a final agreement to satisfy all work packages or all applications or projects.
Okay, thank you, that's clear. Any other questions? It is now or never. Don't be shy again. I'll give you another 5-10 seconds, and otherwise we will say thank you to Roland, and we will move to the next and last presentation for the day.
Okay.
Okay, that's clear.
So thanks again. It was
Thank you.
to participate in this short presentation. And
Yeah.
If you have any further question, you know probably where to find us.
Yeah. Thank you again, Roland, and thank you also like for the others to the TMS team working together with you on this. And as I said, it's now time to move to the next and final presentation. We're closing the day with a double act, just like how we opened the session today. We're gonna have Marcus Vichy from Siemens and Claudia Lutz from Thales, who are going to present the current status of where we stand on the work of cyber securing railways. I see Marcus is there and ready to go. I will give him the control. I know that he's starting the presentation, and Claudia should be joining us by phone, and she will continue.
Yes, I'm here.
Yeah. Hello, Claudia. Marcus,
Hello.
I'm giving you the control, so you should have them now.
Thank you.
And yeah, perfect.
All right.
Now. Thank you very much.
So, topic cybersecurity, really a quite complex topic. I always call it four-dimensional change management, something that people say is nearly impossible because we have not only look at technology, but also in processes and organization, in people, and also the market will change. And cybersecurity drives change in all four dimensions. We present here only two topics of this whole complex topic. One is a more technical topic that I will cover, showing how we go into the technical part for the security architecture and protection profiles. And then 10 minutes later, Claudia will look into some of the process topics. This one is the secure verification topic. We started in Shift2Rail with quite a large group of participants, the who and who in the rail automation business. From solution providers, we have all key stakeholders on board: Alstom, Bombardier, AZD, CAF Signaling, Hitachi, former Ansaldo, Kontron, Siemens Mobility, Thales, and Mermec. And we have also the rail operators there. Deutsche Bahn is there, SNCF, Network Rail, and Traffic Verkehr. Also, Railnem from France for the resource organization is helping us. What have we achieved so far? In Shift2Rail 1 took 3 years with a lot of discussions, but finally we concluded that we found one international standard that can be applied in full to the rail automation domain, and that's the IEC 62443, an industrial security framework. Specifically, we looked at 4-1 and 4-2 for the basis of the security by design. 4-1 is a secure development process that can be completely adapted to also rail automation, so it doesn't conflict with any of the standards that we have in the Senelec that also apply for the software development. And the 4-2, which is a set of technical security requirements. This has been also agreed that this is the basis for the security design. In the standard, we have different levels of security, from a low security level protecting against simple attacks like from kids to more higher sophisticated attacks. And it was after a higher level risk assessment and then several detailed risk assessment concluded that the target security level for the rail automation system should be security level 3. There are 2 other zones which are external outside of the signaling system that has a lower security vector and target level. What we have now looked in at Shift2Rail 3, since we concluded now what the target is for security level 3, we defined the security environment, and we saw also in the TMS section before a little bit of this environment, maybe coincidentally. This is the environment for the next generation rail automation products, so the future. There's a second track in our work package that looks at the legacy system, but the talk that I'm doing here is about the next generation. And here we define shared security services, and I'll show you what this will be. This is an infrastructure that we expect then at every operator, so we have an interoperability between the different markets in Europe. To ensure this interoperability, we also investigated and selected protocols to connect to these shared security services. So we really create an EU interoperability standard. And to formalize this approach, we define protection profiles for trackside and onboard devices based on the selected protocols for the shared security services. This was quite interesting because as these shared security services don't exist at the moment, we had kind of a green field. With these protection profiles that will be public available documents coming up for review now in November and then hopefully published in December, we will start then this as an input for wider EU standardization. For example, in the ERCC TSI, the UNISIC or the EU links organizations. What is the actually defined security environment? As I said, the basis was the IEC 62443 standard. When you look at security level 3, you see that there are essential services that needs to be there, that rail automation products like interlocking, RBC, track objects, and so on, TMS can connect to. This is a system-wide time service, a central logging instance, a security incident and event management system, a SIEM, intrusion detection and continuous monitoring system, an IDS, an identity and access management system that does all the central authorization and authentication, backup system and asset inventory. And the standard doesn't really require certain service, but they're highly recommended in larger installations to have more automation and not to have manual security. These services consist in the public key management infrastructure and the central software update system. We come now to all these services. We need to define the interfaces, and for this we define the selection criteria, that these protocols should be already international standards, nothing proprietary. That means we can refer to a published document, that the document is stable, it's already widespread use. Ideally, there should be an open source implementation available. And since we are talking about security, the protocol should support also authentication and integrity protection with cryptographic means. Further, when we need confidentiality, which is not most of the case in rail automation, not the case, the protocol should support also encryption. And this is when we transfer secrets, for example, or keys. And we look also at historic vulnerabilities and availability of patches. The result of this was that we came up for a couple of protocols, NTP version 4 for time synchronization, syslog over TLS for central logging, same for security and event management system, the certificate management protocol, CMP, that's already used in ETCS, is used here again for identity access management, the SCIM over TLS, L-Sync over SSH for backup, and OPC UA for software update and asset inventory. When we look now at where we are in the final days of review of the internal work packages for the different protection profiles, and they will go into a wider Shift2Rail review in November. From there, we will publish these trackside and onboard protection profiles. And in December, January timeframe, we will start the dissemination to EU standardization bodies like the ERA for the TSI update, the UNISIC bodies, and the EU links. That's from the technical side, and I would hand over now to Claudia, that she looks into the process topic, especially about the verification processes.
Thanks very much, Markus. Thanks a lot. Leah, can you overtake the slides, please?
Yes, I can. Otherwise, Markus can do it. But I can.
Markus can do it. Whoever wants it.
I will.
We are on. Can we go to number 10, please? I can't see it, so you have to just say yes.
It's okay.
Okay, so thanks, Markus. And let's move from the technical to process innovation in context of product security verification. I will start with a small example. Below, you see a security configuration compliance test report showing the security by default of an operating system that was released in November 2019. 28 rules were passed for the configuration, 51 failed. This quick test shows that the targeted operating system does not conform with the European Commission Cybersecurity Act which states that organizations should configure the products in a way that enable the first user to receive a default configuration with the most secure settings possible. So security by default. So let's have a look what security product verification in the future should look like. Can we go to slide 11, please?
Yeah.
Lea, can you go one slide back, please? Yes.
Okay, thanks. Task 9.2 in context of cybersecurity does deal with the verification in the product lifecycle. So it's not project, but product. So as long as a product is in the field. We had actually specified 3 main objectives. So the first objective was, as an outcome of Shift2Rail 1, to analyze in depth this IEC 62443-4-1 requirements on security verification and validation testing and its main test methods. The second one was, which is a logical outcome of the first, yes, to have the same time to have a look at the certification frameworks from ISA and IEC. ISA actually does publish these documents already and does frequently update these documents as well. So these requirements from the standards or certification frameworks are well known to us. And for this reason, they give us some important input we need for our work. First, they provide the interpretation on the security requirements in an objective way. So, I mean, if you interpret security requirements, it can be very subjective, yes. So for this reason, it's good to have a standardization framework in the backend. So this is more product independent, this is more objective and a longer lasting view. And a third, we have an early preparation for the possible conformity assessments we will face for cybersecurity, for railway products in context of the Cybersecurity Act in the future, yes. Because this act is in place since 2019 and might be target railway certification for critical infrastructure. So, and the third topic is actually an enormous field, difficult to overview, that should focus on best practices for the major issues we currently see for the railway business. Due to the time constraints we have here for the presentation, we just focus on objective 1 today. Slide 12, please. So on slide 12, you see that we have, before we start actually with security verification testing, we should talk shortly about the environment of this testing, which is quite interesting. Because from the perspective of the IEC 62443-4-1, you have altogether 8 security practices, so security verification, validation, testing is just one of them. And by this, you have a process defense and depth approach, which is really mandatory for security. So it's not only about testing something, but it's also having security management in place, having security requirements specified, having a secure design, doing a secure implementation, dealing with or managing security-related issues, as well as doing security update management and provide security guidelines to the customers. Second, we have an holistic approach in X-Ray 3. We had it in X-Ray 1 as well. But in X-Ray 3, we additionally have 2 tasks which are dealing with product verification as well. So we have the security verification in the ICS lifecycle there. So this is the upper layer of the system integrator and later on asset operator until decommissioning of a product in the field then. And on the other hand, we have this enormous important topic on supply chain security, yes, because we see much more attacks on the supply chain today than we have seen before. And I think for this reason, we tackle this topic as well. So this is task 9.3 and 9.4 in the current Shift2Rail project. And of course, this approach takes into account that there is a single European railway area. So we do not talk about borders, but we talk about finding a joint approach for cybersecurity. The third environment is, of course, the security conformity assessment, certification, law and regulations. Yes, especially because we are part of critical infrastructure. So as we already said, we have this IC standard 62443. This is a whole series which has standards for all roads, more or less. Then on the other hand, we have European law and regulations like NIS Directive Cybersecurity Act, which are quite new as well. Then we have the domain-specific TS, which is still in the pipe, the TS 5701 on railway application cybersecurity, which probably will be published or voted now and published in 2021. And the TSI 2022 probably as well. So besides this, we have national law and regulations, of course. And last but not least, we have a very important topic we should never oversee. This is the capability of security to integrate with the RAMS process. So we are not, we are a security, we have a security process, but we have to integrate with the RAMS processes, of course. And besides this generic frameworks, we have, of course, a specific requirements and from our customers for interoperability, usability. We have company policies we have to follow, and we have the specific hardware protocol or operating system requirements from the customers we see in context of security. And of course, we should not forget the people who do the work in the labs. So we have operating system skills testers who really are good in testing operating systems, and other which are better in testing web applications. And you shouldn't let somebody who's good in testing web application test them operating system. This is probably not the best way to do it. So let's go to the next verification and validation testing slide. So where we come to the requirements of the standard itself, so of the practice 5. You see we have three perspectives. We have the defender, the attacker, and the organizational perspective. So let's start with the last one. The organizational perspective is really good. We have the independence of testers given in the 4-1, and this is completely in line with the EN 5128. Once you have a look at the defender perspective, this is a product internal view. So this actually security requirements testing, the first one, targets the technical component requirements and customer requirements, of course, as well, which were reported already by Marcus and given in the protection profiles. So we do some functional testing of the security requirements, which is quite known to us. But of course, we also have to do performance and scalability testing. And there we already put a warning, because in this context, you really have to check that the RAMS support of the essential functions. Yes, the essential functions of the system have to be supported, and these are not the security function, but usually the RAMS functions. Yes. So let's go ahead. So we have SVV2 with threat mitigation testing. So we have to ensure that each mitigation implemented to address a specific threat has been adequately tested. And we have, of course, to ensure that the mitigation works as designed. And B, we have to attempt to thwart these mitigation as well. So this is completely new to us. And there's another warning on it, because this depends on the maturity of the threat model. Yes. And I think the standard, it does not specify how to do your threat model, but I think there are various methods, various techniques, and I think threat modeling is one of the most important things. So, and the testing depends on it, but this is the input for the testers later on. So we do not talk about SCV3 directly now, because this is on the next slide, because it has a red flag or red light, whatever. But we go directly to the attacker perspective, so the product external view, so which is called penetration testing, usually widely known. But this is just to know for everybody, this is just a change of the perspective. Yes, the methods used by the penetration testers are the ones we already have in SCV 1, 2, or 3. So they perform their tests, the penetration testers usually, and they widely overlap with this ones we do in the defender perspective, except of course for the findings, because once you have a finding, this indicates a test is or was not or only partially performed, or had the wrong parameters, or a requirement was just not addressed, or example, the coding rules were not reviewed, would be a requirement as well anyway. So the warning we have there, that the railway business does not share any penetration test criteria today. Nevertheless, penetration testing is usually addressed explicitly in all tenders. So last but not least, let's go to vulnerability testing, which is the defender perspective again. So this is a broad definition, which is not often not known by the people. So, and for this reason, we have a lot of requirements or sub-requirements. So we have this abuse case testing or abnormal use case testing. We have attack surface analyzers or scans usually. Then we have this non-vulnerability testing, scanning, and software composition analysis, SCA, and dynamic runtime resource management testing, or DAST. So usually, and this is a major issue, vulnerability testing is often limited to SVV3C. Yes, so people, once they talk about vulnerabilities, they talk immediately about the common vulnerability enumeration testing. And even when this would be the case, then there are many, many questions we have in this case. So which or how many known vulnerability databases to be used? The NVD database from the US, the CERT IST database from France, the DFN-CERT from Germany, or the various product CERT, or any other national CERT, whatever. Question number 2, do we base our common vulnerability scoring system on the severities of the base metric or the environmental metrics? So the base metrics is usually the one which is published. The environmental metrics, they really investigate a CVE directly in the environment where the product or the vulnerability is deployed, in order to see which is the severity which comes up later. Usually you lower the result by this. Question number 3, what happens when penetration testers come along with a zero-day exploit that is not contained in a known vulnerability database? And question number 4, example, how to deal with known vulnerabilities published after code freeze for safety critical certified products. These are all questions which are not answered currently. And for this reason, we share no common view on vulnerability testing within railway business, and this puts our business on a higher risk than necessary.
5 minutes left.
Easy. So our first deliverable will be published in February 2021. It's foreseen, it's 9.4, part 1, product security verification best practices. And we can start with the dissemination immediately after this in March 2021. For example, as input for rail automation certification scheme, but also for further discussion with industry stakeholders. Thanks a lot for your attention, and I warmly welcome your questions.
Thank you very much, Marcus and Claudia. Any question? I'm going to open the Q&A and see whether there are questions. I see there is one for Claudia from Wayne Watson. Claudia, would you recommend the vulnerability testing, on a live system or only against a reference system? People are very nervous about testing live systems.
Yes, I agree. I think it's not foreseen that you do this on staging systems. Otherwise, you really had to head and to assess the risk. Yes, but I think you never do this. You have we have in the 4-2, we have a verification task so that you really verify your system during operation. But even this is in the basic requirement. They say, okay, go to a specific mode, yes, and do the verification then, and then go back to operational mode. And I think there's on security level 4, there is this that you have to be able to do some verification tasks during operation, yes, but I think vulnerability testing I wouldn't do this way. And there must be a staging process, yes, and I think if you look at the standard itself in the 4-1 and the 2-3 and the 2-4, there's always a step in between, and there's even a patch state model, and there are testing activities on product supplier side or system integrator side and on asset owner and operator side beforehand.
Okay, thank you for answering. Any other question? This is the last presentation of the session. You are free to ask whatever question you have while we still have Marcus and Claudia on the line. See, there's no other question in the Q&A as such. I'm looking to see whether anyone has raised their hands. For the moment, no. I see that confirmation that people are very shy when we move online. Any other question on cybersecurity, which is definitely an extremely important and sensitive on many levels topic? I'll leave everyone a few seconds. Otherwise, we're gonna close this presentation there. In the meantime, I'd like to thank Marcus and Claudia for your joint effort and the presentation today. Thank you a lot for this, and of course, just like for the other presenters, thank you also for the experts who are part of the Shift2Rail team on cybersecurity and for the hard work since the beginning of the program. All right, if there is no other question on cybersecurity, it means that we are getting to the end of our session this afternoon, and this closes the IP2, so signaling and traffic management specific parts. I'd like to thank, first of all of the speakers for their availability, the preparation, and the attendance this afternoon. I think it was greatly appreciated by, well, not only by me, but also by the audience, I hope, and I am sure. I also would like to obviously thank the audience. I see that we had quite a high attendance for most of the afternoon. So thank you also to everyone. I hope that you found those presentations and those reports were not only interesting, but also valuable in terms of getting to know a little bit more what Shift2Rail has been doing over the past few years, and specifically what is coming and for the end of the program. I think it was a good snapshot, even though we could have spent definitely much more time for each of the presentations in going into the more details. But I think it gives a good snapshot at what has been done so far in Shift2Rail in this regard, seeing what the future of signaling could actually look like. And also without mentioning how the future of ERTMS, ETCS, as we have seen at the very beginning of the session, will also look like, because there we are also feeding the regulatory framework next year. So we're having very, very tangible results. So I really hope that you've had a good time, even if it was virtual. And obviously, all of the presentations will be made available on the Shift2Rail website in the next coming days. So you will have the chance and the opportunity to look again and explore more some of the aspects. Do not hesitate to contact me directly. I am the program manager in charge of IP2. So if you have any questions, any follow-up in the next few days or next few weeks, do not hesitate to contact me directly as well. I'll be happy to answer or happy to put you in contact with the right expert. And I will close this session for this afternoon. We're finishing a few minutes early. I think it will give you an extra few minutes of break. I'd like to remind you that at 5:45 we'll have a webinar session on Hyperloop together with our executive director, Carlo Borghini, and my colleague, Goras Marinic. So I also encourage you to have a look and a peek into this session. I think it's going to be quite interesting. And I'd like to thank everyone again, and I wish you a nice end of day, end of afternoon, and looking forward to seeing you all at some point again, hopefully next year. Thank you very much.